With the landing of a probe on Comet 67P, the European Space Agency has achieved the most complex space mission of the century, but it has not all been according to plan. The early days of rocket technology were littered with spectacular failures. Cold War adversaries, the Soviet Union and the United States, were in a rush to acquire missile technology to deliver the newly developed hydrogen bomb. During the Second World War, Germany had been working on ballistic rockets. Many of their early attempts had also been unsuccessful. By October 1942, the German team, led by Wernher von Braun, had a workable prototype. When the weapons went into mass production, V-2 attacks were launched against Britain and Belgium. With the fall of Berlin, Russia and America were keen to get their hands on V-2 technology, and German technicians captured at the end of the war were vital to the early rocket programs of both sides. In the 1950s, the Soviet Union began work with clustered engines, and the R-7, the forerunner of today's Soyuz, emerged. The new R-7 featured 2 central stages flanked by 4 boosters, a configuration that's still used today. It could deliver a heavy thermonuclear warhead to a target in North America. And the R-7 was powerful enough to put a satellite into orbit. On October 4th, 1957, the Soviet Union launched an 83-kilogram satellite called Sputnik, and everything changed. As it orbited, Sputnik transmitted a beep that could be picked up by radio as it passed overhead. America took this as a direct challenge. The US had 2 candidates close to launching a satellite. An Army team with its Jupiter C missile, headed by German V-2 engineer Wernher von Braun, and a naval team called Vanguard. Compared to the Army's Jupiter 1, Vanguard was largely unproven. But because the US was reluctant to rely upon von Braun and his German team, Vanguard was given the task of launching America's first satellite. However, the Russians had a new surprise. 1 month before Vanguard's launch date, and barely a month after Sputnik's flight, another R-7 was on the pad. This was the launch of Sputnik 2. And this time there was a passenger, a terrier called Laika. In the US, Cold War paranoia was becoming extreme.
Gets the American people alarmed that a foreign country, especially an enemy country, can do this, and we fear this.
Pressure was building on the Vanguard team to salvage American pride. In addition to the reporters and photographers covering the event, it was announced the launch from Cape Canaveral would be screened live. It was a national humiliation.
And here, Pickering, Van Allen, von Braun.
Von Braun's team was given the go-ahead. In weeks, the group developed a satellite named Explorer 1 that was a fraction the size of Sputnik.
Jupiter C.
Unlike Sputnik, which just carried a radio transmitter, Explorer 1 contained a scientific payload. The Juno 1 was a modified Redstone rocket with a rotating upper stage, a simple technique devised by von Braun for doing away with a final stage guidance system.
The 4-stage Jupiter C in the tense period before time zero at 10:48 p.m. The last 3 stages are set spinning on takeoff for guidance purposes.
It was simple, but it meant that Juno could not deliver its payload accurately to a circular orbit. But the Americans were in a hurry.
In 1958, free men everywhere lifted their gaze to Freedom's satellite.
Later in 1958, President Eisenhower established a civilian-led space agency which absorbed much of the Army missile unit as well as the Vanguard program. It would be known as NASA. In 1959, NASA selected 7 astronauts for a manned space program, which only existed on paper. Russia also had selected a cosmonaut corps and was working to put the first man into orbit. The research, backed by huge engineering budgets, was becoming a proxy war between the superpowers, and so far the Soviet Union was winning. But NASA had inherited the X-15 program, a rocket-powered aircraft that was delivering valuable data about flight control at the boundaries of the atmosphere. The X-15 glided back to the ground without power, and the techniques gathered here were of benefit to NASA when the space shuttle was in development. One of the X-15's pilots would join NASA in its second intake of astronauts. His name was Neil Armstrong. But the Soviets were forging ahead. After several mishaps, they had returned a pair of dogs, Belka and Strelka, safely from space. And in 1961, they were preparing to put a man in orbit. On the 12th of April 1961, a young Air Force pilot climbed into his Vostok 1 capsule. His name was Yuri Gagarin. The first man in space. The Soviet Union had set the most prestigious record yet. The United States had a spacecraft, the Mercury capsule, but they needed a heavier booster to take it to orbit. Explorer 1 had been lifted by a Redstone derivative, and early unmanned Mercury flights would also use the Redstone. Alan Shepard was due to make America's first manned spaceflight, atop a Redstone, but it would be a suborbital flight. The new, more powerful Atlas would take the first astronaut into orbit, and so far, neither launcher was performing reliably. Finally, in May 1961, after a chimpanzee had tested the Mercury-Redstone combination, Alan Shepard would become the first American to fly in space. The flight lasted 15 minutes. Shepard and his Freedom 7 capsule were picked up 480 kilometres off the coast of Florida. Later that month, America's newly elected President Kennedy committed his country to a landing on the moon.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
It was the beginning of the space race, the most concerted scientific effort in history. Since the 18th century, when William Herschel discovered Uranus, telescopes have been getting bigger. Increases in size allowed us to see more distant objects. But it was not until Edwin Hubble that we learned just how distant some of these objects were. It had been thought that our galaxy was the universe until 1924, when Hubble proved that we were just one of countless galaxies in the universe. But astronomers were reaching the technical limit of their instruments, not because of their size, but because of distortion from the Earth's atmosphere. In 1946, astronomer Lyman Spitzer proposed an orbiting telescope above the distorting veil of the atmosphere. It was a wild idea, years ahead of humanity's technical capability, but it was built, and the space telescope named after Edwin Hubble has been in orbit since 1990. No single instrument has contributed more to our understanding of the universe than the Hubble Space Telescope. But it hasn't been straightforward. Something as complex as an autonomous telescope located in the harsh environment of space needs regular maintenance, and it was only possible because of the Space Shuttle and its ability to serve as a work platform. Without the Space Shuttle and its regular servicing missions, Hubble's initial design inadequacy and a series of component failures would have left it as a very expensive piece of space junk. After Discovery's deployment of the Space Telescope in 1990, there were 4 subsequent servicing flights. Hubble was both repaired and upgraded on these missions.
As the vehicle passes through the area of maximum dynamic pressure.
Atlantis, Houston, no action.
With the shuttle now withdrawn from service, there will be no more on-orbit maintenance. Components readied for Hubble's last servicing mission included new gyros, batteries, fine guidance sensor, astronaut tools, support hardware, a new docking ring, the carrier systems, and 2 new instruments. But building the hardware and packing it for flight to orbit was just a part of the preparation. At NASA's Neutral Buoyancy Laboratory in Houston, mock-ups of the shuttle's payload bay and the Hubble were available for the exhaustive training the astronauts needed. Conditions have to match those that the astronauts will experience on orbit. Problems encountered in the pool are solved before the team flies. In 2004, when a power supply blew, Hubble lost its imaging spectrograph. Repairing this component was something never envisaged by the telescope's designers, so special techniques and tools had to be developed. As the flight date approached, all the hardware was packed into special shipping containers for transfer to the launch site, where the next phase of the operation began. On March the 2nd, 2004, an Ariane 5 blasted off from Kourou in French Guiana. It carried the Rosetta probe, one of the most ambitious deep space missions yet launched. Recently, it was brought out of a 3-year hibernation.
When I first heard the idea of Rosetta, I thought it would be extremely difficult.
We've never flown a spacecraft to a comet.
Its mission is to rendezvous with a comet, and it has had to travel a complex flight path to get there. Previous deep space probes have carried radioisotope power supplies, but Rosetta is designed with solar panels. It also carries a lander called Philae. The course Rosetta has followed has taken it past Mars and then back past Earth to gain assistance from the planet's gravitational fields. The probe skimmed past Mars at just 250 kilometres. Originally intended to meet comet Virtanen, launch delays meant a new comet had to be targeted. Rosetta reached a maximum distance from the Sun of 780 million kilometres, taking it beyond the orbit of Jupiter. During its cruise, Rosetta photographed asteroids, Steins and Lutetia. Starting last May, a series of thruster burns were monitored by members of the Rosetta mission team. The first of 3 major burns took place, with Rosetta 500 million kilometres away. It used 218 kilograms of fuel and lasted 7 hours and 16 minutes. It brought Rosetta into phase with its target, comet Churyumov-Gerasimenko. Over several months, 10 separate corrections were needed, and by August, the probe was roughly 100 kilometres from the comet. Soon, team members began seeing just what comet 67P Churyumov-Gerasimenko looked like. These pictures are a computer-generated recreation based on the first images of the comet. As it's still a long way from the Sun, no tail has yet developed.
It's only when you come closer to the Sun, this comet activity, this material starts to become active and it's outgassing, and then the cometary tail is formed, and this is what we normally see in the sky.
Because the comet's mass is so small, Rosetta will have to be at a very low relative speed to orbit it. At the moment, the probe is carrying out a series of triangular manoeuvres to track with the comet. Black and white images relayed by Rosetta's navigation cameras surprised scientists, who were expecting a much smoother object where traces of surface ice were apparent. Of 5 possible landing areas, landing site J was selected. For the Philae lander, it had the best combination of solar illumination and radio access to the Rosetta mothership.
The shape of the comet is definitely a bit unexpected. I consider it at the same time fantastic. It's a unique object. On the other side, has posed us some headaches in finding proper landing site because of this unusual shape.
The Philae lander was released from a distance of 20 kilometres. Its 4-hour drop was timed so that it would arrive at the intended area, taking into account the comet's 12-hour rotational period. Philae's 3 legs are tipped with small screws designed to anchor the craft on contact with the surface. On Earth, the lander weighs 100 kilograms, but although Comet 67P is the size of a mountain, its gravity is very slight. At the comet's surface, Philae has a weight equivalent to a piece of paper. This is a problem that leg screws and a small anchoring harpoon were designed to overcome. In addition, a small thruster at the top of the lander would push the craft down on contact with the surface. This is how it was supposed to happen, but scientists, who had to wait for a message relayed via Rosetta, were confused. It took an hour for a confirmation signal to reach mission control in Darmstadt, and initially there was celebration. But after hours of analysis, it became apparent that the anchoring devices had all failed, and the probe had bounced back up to a height of 1 kilometre. After initial contact within 1 metre of the intended landing ellipse, Philae finally came to rest at the base of a cliff. It was functioning well and sent back images of its surrounds, including this picture of its foot wedged up against the cliff. This was not a good place, as the craft's solar panels will receive only limited sunlight. While its batteries still had enough charge, the lander was asked to drill out a surface sample, analyse it and relay the results to the Rosetta mothercraft. This went smoothly, but Philae's batteries are now flat. It is hoped that as the comet approaches the Sun, the craft will receive enough light to recharge its power supply. Meanwhile, the Rosetta probe will continue to follow Comet 67P as it warms and develops its characteristic tail. Since the earliest days of rocket launches, thousands of satellites have been delivered to Earth orbit. Today, an awareness of orbital debris means satellites at the end of their lives are set on a course that will see them burn up in the atmosphere. But many satellites remain aloft, and upper stages containing unburnt fuel will continue to drift, sometimes with alarming consequences. A cloud of orbital debris has been building up around our planet. This has serious implications for new satellite launches. ESA tracks the larger pieces of this orbital debris to see whether current satellites are in danger of collision. ground stations are important in determining the orbital parameters of defunct satellites that can no longer communicate. Only 7% of monitored objects are functioning satellites.
Of the 16,000 to 17,000 objects that we can track from ground stations up there, just about 1,000 are operational spacecraft. All the rest are remnants of past spaceflight activities, and more than one-half of these objects are in fact fragments from on-orbit collisions recently, and also fragments from on-orbit explosions.
Satellites at the greatest risk are those in north-south orbits, like the Earth observation satellites. The tracks of these craft converge at the poles, and this is where the highest likelihood of collision exists. There have already been 4 major collisions in low Earth orbit. The most serious impact was the one between an Iridium satellite and a defunct Cosmos satellite in February 2009. They collided at a relative speed of around 42,000 kilometers per hour, creating an additional 2,000 pieces of debris. This debris cloud has continued to spread across different polar orbits. According to international space law, responsibility for any debris or abandoned satellite remains with the owner. Regulations require new satellites to carry enough fuel to enter a decaying orbit at the end of their usable life. Schemes to deorbit dangerous objects are being devised, but they are very expensive. Russia's Soyuz launch system is the result of more than 50 years of gradual evolution. It's the world's most reliable rocket, having flown more than 1,700 times, and commercial users love it. In the 1950s, when the USSR and the USA emerged as post-war superpowers, ballistic missile technology was pushed centre stage. Early results were frequently catastrophic. Because America could station missiles in Western Europe, they developed short-range weapons. But the Soviet Union had to develop the capability of delivering a heavy nuclear payload from Russia to the United States. The R-7 Semyorka was the world's first intercontinental ballistic missile. It also gave the USSR the ability to launch a satellite into orbit, a huge advantage in the early years of spaceflight. Americans were alarmed when their communist enemy began setting space records that were years beyond their free market technology. In 1958, President Eisenhower established NASA to consolidate America's space effort in one civilian agency, and the newly assembled team started work in a hurry. The overwhelming feeling in the US was they were well behind the Russians. NASA absorbed the US Air Force's Man in Space Soonest program. It was renamed Project Mercury. Engineers began work on a titanium space capsule that could sustain a human in the vacuum of space and withstand the searing heat of re-entry. As prospective astronauts, 110 military test pilots met NASA's basic prerequisites and were invited to enter the rigorous selection process devised to choose the Project Mercury team. As well as being a qualified jet pilot with 1,500 flying hours, applicants had to have an engineering background and be younger than 40 at the time of selection. But some pilots were reluctant to volunteer, feeling that astronauts would do little flying, simply serving as glamorized lab rats. When the first 7 astronauts were introduced at a press conference, they were lauded as movie stars. It was 1959, and the only living thing to have orbited the Earth was a Russian dog. It was known that the Soviet Union was working to get a man into space, but NASA was determined that an American would get there first, so they began modifying the proven Redstone booster. Although it did not have the power to launch a man into orbit, they planned to make a series of short suborbital flights to test their technology. NASA's first manned orbital flights would use the SM-65 Atlas missile, a much larger ICBM that was being modified to carry the Mercury capsule. But reliability was a problem. In September 1959, during the static test of an Atlas, a turbopump failure triggered a complete shutdown. But fire persisted. The damaged pump was leaking oxygen. Damage to the pad took 7 months to repair. Because so many boosters were blowing up, an emergency escape system was developed. A tower atop the capsule housed a small but powerful solid fuel rocket that could pull the spacecraft clear of a catastrophic failure. To test the escape system, a new booster known as Little Joe was built. It was based on existing technology and cheaper than using a full-scale rocket. The escape tower was tested on the ground at maximum dynamic stress and at very high altitude. A complex sequence of events had to happen automatically to return the capsule safely to an ocean splashdown. This would give problems at a later stage of testing. The capsule itself had to be tested, and the new astronauts were each given an area of specialisation. Engineers would get direct input from the people who would fly the Mercury spacecraft. At NASA's Langley Research Center, the new astronauts were schooled in concepts such as retrofire and re-entry. The Mercury 7 all had engineering degrees, and even at this stage, their feedback was leading to redesign of capsule control systems. Simulators were developed that gave an astronaut the sensation of a tumbling capsule, allowing the team to gain experience before they flew. On special flights, they had a taste of zero gravity. Towards the end of 1960, the Mercury team was nearing full-scale flight tests. The first Mercury-Redstone combination would make an unmanned suborbital flight to qualify the system. Alan Shepard had been selected to make the first manned flight, and it seemed he would be the first man in space. Known as MR1, this first Project Mercury vehicle was assembled at Cape Canaveral's Launch Complex 5. It would test the automated flight control, the launch and tracking system, as well as recovery procedures. The capsule's automated abort system, a vital safety feature, would also be tested. It would be known as the 4-inch flight. The booster engines abruptly stopped, and the escape tower was jettisoned as programmed at the end of the boost phase. This triggered the deployment of the parachutes, leaving the capsule in place atop the fully fueled Redstone. The problem had been caused when power plugs at the base of the Redstone disengaged in the wrong sequence. A technician had filed down a contact to make it fit. A new booster was flown in to replace the damaged one. The same capsule would be used for the second attempt, but it had to be refurbished. The electrical connections that had triggered the engine shutdown were redesigned, and the automated sequencing for jettisoning the escape tower had been rethought. Main engine cutoff could only trigger the release of the tower 137 seconds after liftoff. The delayed flight, now known as MR-1A, was launched on December the 19th. It flew higher than expected, but was otherwise flawless. Yet NASA had lost a month in their rush to put a man in space first. A chimp would make the next flight. Engineers were uncertain about risking an astronaut when the booster was still flying too high. Chimp number 65, known as Ham, would fly before a human, and the astronauts were not happy. The flight was designated MR2, and if it all went well, Alan Shepard would be next. But things did not go well. An overactive pump depleted the engine's liquid oxygen too quickly, and when the engine pressure dropped, the escape system kicked in, lifting Ham's capsule to an altitude of 253 kilometres, far higher than had been planned. Because the escape system had activated, the capsule's retro rockets had been jettisoned, meaning the spacecraft's ballistic return to Earth could not be slowed. Ham, the Astro chimp, experienced more than 14 G during re-entry. Next, a valve opened early and the capsule lost pressure. Finally, when the capsule splashed down, 200 kilometres beyond the planned point, the impact bag was shredded and the heat shield had punched holes in the capsule base, flooding it with seawater. Ham had survived, protected inside the small compartment which functioned as his spacesuit, but debate about whether the system was ready to take an astronaut began. An extra flight to sort out the bugs in the Redstone booster was scheduled. At the same time, NASA was preparing the much larger Atlas booster in readiness for orbital flights. Developed as a weapons delivery missile, the Atlas was also being used to launch satellites. Its very thin stainless steel skin made it very light, but it was also fragile, and its early safety record was not good. At its first launch, carrying a dummy Mercury capsule, the Atlas's thin skin buckled. It would be strengthened for all subsequent flights. It had not been publicly announced that Alan Shepard would make the first Mercury flight, but team members were growing in confidence that he would become the first man in space. But his flight was postponed several times. A replacement for the booster needed for the extra development test was slow in coming. An original launch in February 1961 was put off till March, then to May. In April, the Soviet team had yet another surprise. After a heartfelt farewell, Colonel Yuri Gagarin prepared to enter his Vostok spacecraft. The flight and Gagarin's identity had been a closely guarded secret, with none of his cosmonaut colleagues being aware who was to make the first attempt. The craft would function automatically, with Yuri Gagarin needing to enter a code to unlock the controls should it be necessary. Gagarin completed one full orbit of the Earth and returned safely. He was only in radio contact while flying over Russia. The first cosmonaut was a hero. The first manned spaceflight captured the world's attention, and it surprised the Soviet Union as much as anyone. The smiling Gagarin became a huge asset to his country. The Soviet leaders wanted more, and government funding for space was assured. One group not happy about Gagarin's flight were the Mercury astronauts. While they were getting plenty of publicity, all they had done so far was train. Alan Shepard had missed the opportunity to be first, and his short suborbital flight would be an anticlimax after the Soviet triumph. In the early hours of May the 5th, 1961, Shepard arrived at Cape Canaveral's Launch Complex 5. A Redstone launcher stood waiting, topped with a Mercury capsule Shepard had named Freedom 7. It was a pointed dig at the Soviet Union's political system. American media had branded Gagarin's flight as a propaganda stunt rather than a scientific achievement.
3, 2, 1, 0. Liftoff. All right, liftoff, and the clock has started. Yes, sir. Reading you loud and clear.
After a delay, Freedom 7 blasted off. The flight climbed to a height of 187 kilometers.
PSI, oxygen is go. What a beautiful view.
At several points, Shepard took manual control of his craft, but it was over quickly, with the flight lasting just 15 minutes and 22 seconds. Freedom 7 splashed down in the Atlantic off the coast of Florida. Though Shepard had not orbited, Project Mercury had put a man in space, and America was keen to catch up. The idea that there was a race between the superpowers was becoming all too clear. Launched in June 2003, ESA's Mars Express reached Mars in less than 7 months. It took advantage of the planet's closest pass by Earth in 60,000 years. It was the European Space Agency's first mission to the Red Planet, and it rose from the ashes of Russia's failed Mars 96 mission. Europe had made a major technical contribution to the Russian probe, but after a successful launch, the 4th stage failed to reignite, and Mars 96 burned up in the Earth's atmosphere. Though there is no outward similarity between the probes, Mars Express contains many of the same sensors and instrumentation as its Russian predecessor. Since its arrival at Mars, the probe has been imaging the Martian surface. Its instruments are designed to find out more about the planet's atmosphere and its geology, including evidence of surface water that may have existed in the past. Contour images of the surface reveal features that are familiar to us as having been caused by volcanic eruption, but all tectonic activity has ceased long ago. Mars shows signs of erosion too, yet the channels have long since dried. But the fact that water once flowed here may mean that rudimentary life got started. Just like Earth, Mars revolves on a tilted axis, giving it seasons, but because the planet's orbit is highly elliptical, there is broad variability in surface temperatures. In summer it can reach 20 degrees Celsius, dropping to -90 overnight. Mars also has polar ice caps, but they're made of water ice covered in winter by a layer of frozen CO2. This layering process is not fully understood. Instruments on Mars Express suggest that the thin atmosphere is 95% CO2 with traces of nitrogen, oxygen and water vapour. It supports fine cloud and strong winds. Now, the only forces able to affect the surface topography are dust storms and meteor impacts. Mars Express is in an elliptical orbit around Mars at right angles to the orbit of Phobos, Mars's major moon. Recently, it made its closest approach to the tiny moon, which is too small to have a spherical shape. Phobos has the appearance of a captured asteroid, but scientists are puzzled by it. Its mass and density are lower than expected, so it's thought to be porous. Since it has been in orbit, the infrared spectrometer on Mars Express has continued to discover water, which has planetary researchers upgrading their expectations that some form of life may once have existed on Mars. Mars Express has had several mission extensions. New measures have been instituted to conserve the spacecraft's dwindling fuel reserves, and it looks like the mission will continue until its fuel finally runs out. Russia's iconic Soyuz launcher at the Baikonur Cosmodrome. Currently, it's the only means of taking cosmonauts to the International Space Station. What makes it special is its direct lineage to the historic designs that launched the first satellite and the first man in space. The most striking outward similarity is the 4 strap-on boosters. Together, these make up the first stage. The central core around which they cluster is known as the second stage, even though it ignites before launch along with the strap-ons. These stages are fueled by kerosene with a liquid oxygen oxidizer. After 118 seconds, the 4 first stage boosters are jettisoned, and the second stage will continue burning for another 3 minutes. Like other Russian rockets, the Soyuz takes its name from one of its most frequently lifted payloads, the Soyuz spacecraft, which has been in service since 1967. Since the retirement of the US Space Shuttle, the Soyuz spacecraft has played an indispensable role in ferrying crews to and from the International Space Station. With a capacity of 3 cosmonauts, and with the ISS having a working team of 6, there need to be 2 Soyuz spacecraft on hand at the space station in case an evacuation is required. The Soyuz launch system uses very simple production techniques. Unlike the American shuttle and the Saturn V's, the Soyuz is assembled horizontally, which saves a huge amount of extra manufacturing hardware and complexity. Final integration happens on a rail car and incorporates the lifting arm that will raise the rocket at the launch pad. The trip to the pad happens at a walking pace, and it is a Russian tradition that cosmonauts due to fly will witness the rollout. At the pad, hydraulics are used to raise the Soyuz to vertical, where it is suspended above the flame pit and supported by 4 counterweighted arms. Fueling and service gantries also surround the rocket. The gantries will be withdrawn before launch, leaving the unique tulip-shaped configuration. This was originally devised to add extra support to the waiting rocket, as the Baikonur launch site is known for its strong winds. In 2011, a Soyuz launcher was being prepared for launch from a new site. It has been adapted for use at the European Spaceport in French Guiana.
5, 4, 3, 2, 1, top.
With improved lift capacity and an enviable launch record, commercial satellite clients just love the Soyuz.
In 1903, when the Wright brothers flew their flyer at Kitty Hawk, North Carolina, they could never have imagined the ways powered flight would transform the world. More than a century later, the Kitty Hawk Aeronautical Company, named in honor of the Wright brothers, is working on its own transformative technology. Kitty Hawk is one of the pioneers of all-electric vertical takeoff and landing aircraft, also known as eVTOL. Its latest concept is Heaviside, a single passenger plane with a range of 160 kilometers from just one electric charge. Heaviside is 100 times quieter than a helicopter, flying at a sound level of just 35 decibels, a level that is barely discernible to the human ear. With the ability to take off or land in a 100 square meter area that does not need to be paved, the aircraft has many potential applications. As cities become more congested, planners are looking at options such as flying taxis to get people off the roads. Urban aviation has the potential to put everyone in the pilot's seat.
My only dream from my childhood, I remember, was when I could fly, and it was such an amazing feeling that from that point on I just felt it has to be real.
Kitty Hawk's flyer prototype has a control interface so simple that would-be pilots only need an hour's tuition before they can fly it.
Very few of us have a privilege of flying, but now, in less than an hour, you can learn how to fly.
I think everybody on Earth, they dream of flying, especially as a kid. You look up in the sky and you see a bird, or you even have dreams at night where you just start flying. And now with Flyer, we're going to be able to walk out to that dock today, get inside of it, and start flying. I feel completely prepared to get into Flyer and take off. We did the training yesterday, so we did the simulator training, and then we did the strap down where we turned on the vehicle and kind of revved it up, and it was tied down to the ground. I've felt the power of Flyer, and now to take the straps off and just start flying, it's a kid's dream come true. It's a complete breakthrough in aviation, to have something so simple, so intuitive, that someone like me can just get in and enjoy the freedom and the joy of flight.
That was incredible. It's like part of your body.
Yes. Yes.
When it comes to urban mobility solutions, the biggest dream of all is the flying car. Having the option to switch between driving and flying has been part of our vision for the future since flight began. Aeromobile 5.0 is a Slovakian concept four-seat flying car designed for door-to-door flying. When traffic is light, you can stay on the road. If it looks like you'll hit congestion, the onboard computer recognizes the route and sends you to a heliport, where you can launch into flight mode. Powered by an electric motor, the Aeromobile has wings that pivot backwards when the vehicle is in its driving configuration. It has a range of 700 kilometers and is designed to be flown in any weather conditions. If it's able to secure the necessary certifications and permits, the company plans to launch the 5.0 by 2030. So it might not be long before we see cars taking to the skies. Japanese company SkyDrive has a clear vision for how it sees flying cars fitting into our lives.
この先渋滞中、飛行モードを推奨します。飛行可能エリアに入りました。
東京のオフィスまで。
かしこまりました。候補が2カ所あります。
外部ノイズをキャンセル。
かしこまりました。旋回してください。
了解。
SkyDrive sees a future where flying cars are as common as land-based ones.
9時に間に合う？
5分前に到着予定です。
ギリギリだな。
SkyDrive is a Japanese tech startup that's designing another electric flying car. Japan is getting serious about being at the forefront of the flying car revolution. The country has set up a special council that brings commercial operators together with government regulators to work out the practical details of getting flying cars safely airborne. SkyDrive came from a group known as Cartivator, an association of engineers from established brands like Toyota, who worked on speculative designs in their spare time. Now Toyota is a SkyDrive investor, along with NEC and Fujitsu, and a number of Toyota executives have been brought on board as advisors. Thanks to the car company's support, SkyDrive is able to use the 10,000 square meter development base at Toyota City. That includes an indoor flight test facility, one of the largest in Japan. The company is also developing cargo drones with the ability to transport heavy goods and equipment to hard-to-reach places. The global market for flying cars is expected to be worth billions of dollars by 2040. SkyDrive is determined to be one of the industry's main players, and a recent successful manned flight shows it's on the right flight path. Rideshare company Uber is expanding its horizons from the ground to the air. To overcome the gridlock of city traffic, Uber wants its passengers to consider an electric vertical takeoff and landing aircraft as a transport option. By taking advantage of space above the skyscrapers, urban aircraft will reduce congestion and make cities feel more open and accessible. Uber pictures aerial ride-sharing as a way of providing a flight option across a city's busiest areas. The plan is to have customers check in at custom-built skyports located strategically around the city and hitch a ride in an autonomous aerial vehicle which would swiftly take them to the closest skyport of their destination. If necessary, the passenger would transfer to ground-based transport for the final stage of their journey. Uber's Elevate network includes partnerships with 8 of the world's most innovative aircraft manufacturers. They are each developing concepts for eVTOL aircraft built specifically for ride-sharing. Uber Air would be powered by Elevate Cloud Services, a suite of software with the ability to manage dense operations of unmanned low-altitude air traffic. The company is currently using its Uber Eats urban drone delivery service to test its air traffic management system. The top names in architecture, design and engineering are currently working on skyport concepts. It's a big task, as the buildings need to be capable of handling up to 1,000 landings an hour. Boeing is one of Uber's aircraft partners, and its latest autonomous passenger air vehicle has been undergoing rigorous testing. A check of the electric aircraft's autonomous functions and ground control systems saw it pass with flying colours, so it might not be long before it arrives at a skyport near you. The skies of the future will be teeming with drones and autonomous air taxis, as well as airliners. Aircraft manufacturer Airbus is developing an air traffic management system that aims to support the rise in unmanned aerial vehicles needing clear flight paths. The purpose of Airbus UTM, or Unmanned Traffic Management, is to identify the most efficient airspace structures for new technologies. The huge projected increase in small aerial vehicles travelling around cities makes it essential to create a system that enables all autonomous aircraft to communicate their positions with each other, as well as with an overarching traffic control.
The first step to achieving clarity in what are the standards and regulations for autonomous systems is that we need to get everybody together and sharing and open and on the same page. We need collaboration across the industry because this problem is bigger than any one company.
The entire aviation industry focuses around taking small steps first, which is very important. By getting small applications in place, we make valuable learnings, we gain a lot of information, we gain feedback, we gain economic information and viability, and all of that will boil together to produce an even better next iteration as we scale up the services, have more aircraft, and have them do more complicated things.
So it's a really exciting time for the industry. It's really just kicking off. We've done a lot of the R&D, and right now is when real UTM services are starting to be implemented.
The system we put in place today and over the next few years will be the system that's in place for decades to come, and it will affect the next generation of people using the air traffic control system.
As part of its digital transformation, Airbus has invested in touchscreen options for pilots of its A350 aircraft. When combined with the electronic flight bag, they provide easily accessible displays that bring up vital information with just the touch of a finger.
Welcome in the cockpit of the A350 XWE, which happens to be the best cockpit in the sky. The core of this cockpit is made by 6 large, identical displays, which have been developed by Thales. These screens allow to display the right information for the pilot to fly, navigate, communicate, manage the system, as well as with the EFB to manage the mission. This cockpit is the one of our MSN 373 to be delivered to China Eastern. For each pilot, the electronic flight bag is made of an airline laptop racked in a docking station next to the pilot seat. The display can be performed on the cockpit outer screens or something which is unique to the A350 when the pilot selected OIS on center on the lower center display. The control of the electronic flight bag can be obtained via the tablet integrated keyboard or via the trackball controlling a cursor via the Keyboard Cursor Control Unit, or KCCU. The new development made by our supplier, Thales, makes their screens capable to be touch screens. This is a new way allowing interactivity with the electronic flight bag applications, and for the time being only on the EFB applications.
But perhaps this technology is just a stepping stone to something even more advanced. Airbus has spent the past 2 years successfully testing autonomous taxi, takeoff and landing of a commercial airliner, a world first in aviation. This has been achieved through fully automatic vision-based flight tests using onboard image recognition technology. More than 500 test flights have been flown, with 450 of them dedicated to gathering raw data to support and fine-tune algorithms. A series of 6 flights conducted 5 takeoffs and landings per run to test the aircraft's autonomous flight capabilities. In Wyoming, USA, scientists are working to improve weather forecasts.
Mike from Monarch. We're testing a GNSS-RO sensor on board the Atmospheric Research Laboratory from the University of Wyoming. Back there, Brian and Paul from Night Crew Labs, just making sure that everything works. What our flight plan is we basically go up as high as we can on the aircraft, then we maintain altitude, continue a straight and level flight for about 280 nautical miles. We make a U-turn and we come back. The aircraft is collecting multiple channels of atmospheric data, and we're looking at humidity data. We have a vertical LiDAR profiler. We have a cloud camera that's taking pictures of water vapor particles as well as icing droplets.
The sensor payload tested on the mission has the potential to improve the choices we make around weather-related events by adding truth data to forecast models and increasing accuracy.
So how's flying a plane?
That was such a unique experience. That was one of the coolest things I've ever done. God.
One of the things that's so amazing about this trip is that my whole life I've wanted to work in aviation and I've wanted to work on flying laboratories. The view is beautiful outside, but you have a lot of work to do, and you're getting in the console, making sure that all the parameters are coming back correctly, and it's really a thrill. Like I really enjoy it. And yes, we have a lot of flying hours to do. Hopefully I enjoy it by the end, but it's just gorgeous scenery and amazing science. So I am really happy.
Flying be like in the future? How will automation and customized options change our traveling experience? Manufacturers such as Airbus are investigating ways new technologies can be integrated into existing design. One possibility is cabins that automatically reconfigure to accommodate the number of people on a flight. Instead of overhead bins, passengers place their hand luggage in a separate storage area to be retrieved at the push of a button. The ecological self-cleaning seats will morph to suit the shape of the person sitting in them, while a floating touchscreen provides instant access to entertainment and assistance. The engineers who designed this fantasy flight envisage an aircraft that's ultra-long with slim wings, semi-embedded engines, a U-shaped tail, and a lightweight, intelligent body. This design will improve the flight's eco-efficiency, resulting in lower fuel burn, a significant cut in emissions, less noise, and greater comfort. Those planning for the future believe that passengers will expect seamless access to a wide range of technology and applications. Flexibility will be key, so we can enjoy many different experiences on board. Hologram pop-ups take you to whatever social scene you want to experience, from conferencing to virtual meetups. The airliner of the future will not just be a mode of transportation. It will include wellness options that make travel energizing and exciting. Walls that become transparent at the touch of a button, making you feel as if you're floating above the clouds. Holographic projections of virtual decors allowing travelers to transform their private cabin into an office, bedroom, or Zen garden. The aircraft's bionic structure mimics the efficiency of bird bone, which is optimized to provide strength where needed. This allows for an intelligent cabin wall membrane, which controls air temperature and the level of transparency. The cabin's integrated neural network creates an intelligent interface between passenger and plane, and can identify and respond to passenger needs. This includes the opportunity to experience vitamin and antioxidant-enriched air, mood lighting, aromatherapy, and acupuncture treatments, all while taking in the panoramic view. By offering different experiences within each zone, airlines would be able to achieve price differentials and give more people access to the benefits of air travel with minimal environmental impact. While some of these concepts may seem beyond the realm of possibility, the fast pace of technological development means they might just be closer than you think. With autonomous airliners on the horizon and short-hop electric sky taxis waiting in the wings, it won't be long before our skies and our modes of transportation look very different. One option for our aviation future is hypersonic airliners, a concept Boeing has been working on for some time. It could see us crossing an ocean like the Atlantic in under 2 hours.
It obviously looks quite a bit different than what you would consider a normal airplane to be. One of the key differences is what it's made out of. When you're traveling that fast, friction causes the surface to become very, very hot, over 1,000 degrees, sometimes well over 1,000 degrees, depending on how fast you're going. So you can't make it out of aluminum. You have to make it out of more exotic materials. For example, at about 1,000 degrees, you can use titanium. Beyond that, you can use nickel-based alloys, something called Inconel, up to about 1,500 degrees. Beyond that, you have to go to ceramic materials.
At this stage, hypersonic passenger flight is more conceptual than realistic. Airbus sees potential in electric-powered airliners as it searches for ways to fulfill its mission to increase environmental efficiencies. EFAN-X is a complex hybrid electric flight demonstrator that has had one of its 4 engines replaced with a 2-megawatt electric motor. In partnership with engine manufacturer Rolls-Royce, the project tested the possibilities and limitations of a serial hybrid electric propulsion system in a demonstrator aircraft, the first of its kind in the world. More than 30 projects are currently working on hybrid electric power for airliners, and it's hoped the technology could become commercially available in just over a decade, leading to lower emissions and reduced fuel bills. But aviation in the future is not just about repurposing today's technology. Some options might see us reaching even higher than sky.
The very first thing that we did as a company when we started out was we talked to our customers about their expectations for what they wanted when they went to space. And it was those expectations around the rocket ride, the weightlessness, the view of the Earth from space, and the reception of their astronaut wings upon the conclusion of the journey that were the key drivers behind our entire design process.
So, where will you fly tomorrow?
Designed in 1974 and still going strong, the EMU is the spacesuit that astronauts continue to use on the International Space Station. Gemini was the brief but intense interim program where NASA pioneered rendezvous maneuvers needed for lunar missions. In 1963, Project Mercury had come as far as the technology would allow. The final 3 missions were cancelled so that NASA could shift focus to a new program and develop the techniques needed to reach the moon. It was decided that before embarking on the 3-man Apollo program, as had been intended, an intermediate stage to learn about orbital rendezvous and docking was needed.
It was in Houston that Mr. Kennedy emphasized the need for peaceful uses.
It was called Project Gemini, and in many ways, the new program's capsule was more advanced than the Apollo spacecraft that would follow it. It was designed for a two-man crew, and astronauts referred to it as the Gusmobile because Mercury veteran Gus Grissom had played a major role in its development. The Gemini spacecraft would have the ability to change its orbit, and it included instrumentation and systems that were borrowed from jet fighters. One of its most revolutionary features was its onboard computer. It had a memory of just 20 kilobytes. At the beginning, it was proposed that the Gemini capsule wouldn't have landing parachutes, but a Rogallo wing. Grissom was involved in the early tests before this idea was abandoned. It added a layer of complexity that couldn't be easily accommodated in the capsule's design, and NASA reverted to the traditional water landing. To boost the Gemini spacecraft to orbit, NASA hastily adapted the US Air Force's Titan II missile. The Titan II had a much simpler design because it used hypergolic propellant which could remain stored in the rocket for long periods. The two fuel components didn't have to be kept at sub-zero temperatures, but they were extremely toxic and dangerous to handle. Designers understood that any launch mishap wouldn't cause the large explosions seen with liquid oxygen, so they dispensed with the launch escape system used in the Mercury program and equipped the Gemini capsule with ejector seats. Of the original Mercury 7 astronauts, only Grissom, Schirra and Cooper remained, with the rest having left NASA or having been suspended for medical reasons. To bolster its core of space pilots, NASA took in a second group of 9 astronauts in 1962 and another 14 the following year. Before the astronauts could fly, the Gemini-Titan combination had to be tested to demonstrate its reliability. The booster was prone to rapid variations in thrust, known as pogo oscillations. Modifications were made to the rocket, and unmanned flights of Gemini 1 and 2 were made in 1964 and 1965. Mercury veteran Gus Grissom and new recruit John Young would fly the first manned Gemini mission. Because the Gemini craft was fitted with ejector seats, they had special training exercises that involved parachuting into the water. The two astronauts also spent long hours in the Gemini simulator, where engineers could run them through challenging scenarios that may happen in space, while also training mission controllers. The Gemini 3 flight was scheduled for March the 23rd, 1965, and as the launch date approached, publicity became intense. The new President Lyndon Johnson was keen to be seen with the next astronauts. America was gaining confidence about its future in space. 5 days before Gemini 3 was due to blast off, the Soviet Union launched a two-man spacecraft. What nobody was expecting was another record, the world's first spacewalk. Cosmonaut Alexei Leonov left his Voskhod 2 capsule to float freely in space for 12 minutes. In the West, it was perceived as another Soviet triumph. In reality, Leonov's suit had distorted, and he was only just able to get back inside. The whole mission was plagued with difficulties, but these details didn't come to light for decades. For America, Gemini 3 felt like a welcome return to space. It had been almost 2 years since a NASA astronaut had been in orbit.
You're on your way, Molly Brown.
It would be the first of 10 manned Gemini missions. American media was making the astronauts household names. Achievements of the new manoeuvrable craft in space included the first change in orbital shape and the first change in orbital plane. After just 3 orbits, Grissom and Young returned to Earth. During the Mercury program, astronauts had named their capsules. Grissom had named Gemini 3 Molly Brown, after the Broadway show The Unsinkable Molly Brown. NASA did not like this, as it was a reference to Grissom's Mercury capsule that had sunk to the bottom of the ocean. Barely 3 days after their return to Earth, Grissom and Young were at the White House, where President Johnson presented them with NASA's Distinguished Service Medal. Then, something that was to become common across the Gemini missions: a ticker tape parade through the streets of New York. NASA understood that the American public needed something in return for the hugely expensive space program. It gave them a new brand of hero. The next mission, Gemini 4, would be a much longer duration flight. Its crew would be from NASA's second intake of astronauts, Ed White and Jim McDivitt. They had been in training for 3 years. White had been practicing with a special manoeuvring unit that he would use during NASA's first spacewalk.
3, 2, 1, 0.
Gemini 4 blasted off on the 3rd of June 1965. After the previous flight had verified the spacecraft, this mission would work out how to use it. Soon after reaching orbit, the crew located the rocket's discarded second stage and tried to move towards it using visual cues only. But the more McDivitt manoeuvred towards it, the further away the booster got. Rendezvous was going to be harder than it seemed, and Mission Control called the exercise off. There was a more important task. During the 3rd orbit, Ed White opened the door of the depressurized capsule and, using the maneuvering unit nicknamed the Zip Gun, he moved into the void. This exercise had been shifted up the Gemini schedule after the success of Alexei Leonov's spacewalk. Soon, a stray glove drifted from the capsule. It would continue in orbit for another month before burning up in the Earth's atmosphere. The spacewalk was successful, except for a small break in communications.
The flight director says get back in.
This is Jim. What, got any message for us?
Gemini 4, get back in.
Okay. I don't know, we're coming over the west end. They want you to come back in now.
Roger, we've been trying to talk to you for a while here.
Another first for Gemini 4 was that the control centre had moved from Cape Canaveral to a new home in Houston. And because the mission was due to last 4 days, it was the first time that 3 separate 8-hour shifts had gone into operation. There had been a problem with the computer, and the hatch had been difficult to open and close, but as Gemini 4 re-entered the Earth's atmosphere, Mission Control regarded the flight as a success. But they now knew future missions would have to focus on orbital rendezvous.
You ain't gonna do much about it from here on.
Post-flight honours for White and McDivitt included a ceremony at the University of Michigan, where they had both studied. At another ceremony, the President pinned NASA's Exceptional Service Medals on them. The Gemini program was just starting to deliver, but America was still not sure if they were catching up with the Soviet Union. But the future for Gemini seemed bright. Venus is just over 43 million kilometres away. Early astronomers believed it to be similar to Earth. In 2005, ESA launched the Venus Express mission. And after 8 years of close observation, we now know a lot more about our planet's nearest neighbour. Surface temperatures on Venus are more than 450 degrees Celsius, and its atmospheric pressure is almost 100 times greater than here on Earth.
You have clouds that are made up of sulfuric acid, in fact, so it's a very nasty place to be at. And that's one of the big questions on Venus. Why did Venus go that way, and why did we on the Earth go this way?
The planet takes 243 Earth days to rotate on its own axis, and only 220 days to go around the Sun. And its rotation is opposite to Earth's, with the Sun rising in Venus's west. In Venus's upper atmosphere, violent winds blow at speeds up to 400 kilometers per hour, and it has permanent hurricanes almost 200 kilometers across, moving around its poles. Information about the climate and magnetic field has been gathered by Venus Express since it went into orbit around Venus in 2006. It has been made available to a broad cross-section of experts. As Venus Express neared the end of its operational life, its handlers began taking risks, guiding the probe closer and closer to the planet, where it could observe in greater detail. In a maneuver known as aerobraking, the probe edged through Venus's upper atmosphere.
We are going so close that we actually sense the atmosphere as a friction against the structure of the spacecraft, and in that way we can measure densities in the atmosphere of Venus that we have not been able to measure for all those 8 years we've been circling the planet. We also measure magnetic fields with a magnetometer, and we measure energetic particles that we find there. So it's a very new type of measurements and very valuable data we're collecting these days.
In the end, Venus Express exceeded its design brief to collect a new class of information about Venus. This helps us to understand the evolution of our solar system, and, with Venus being very close to the size of Earth, science is gaining an insight into Earth's possible future. Since the earliest days of flights to space, each new spacecraft had a new spacesuit designed specially to go with it. The Mercury program used a version of the US Navy's Mark IV. The Gemini astronauts wore the G3C and G5C, which were based on the suit worn by X-15 pilots. They had to cope with possible ejection and with spacewalks. The Apollo astronauts wore versions of the A7L spacesuit. It had to be able to cope with the lunar environment and protect its wearer during what often looked like hard labour. With the development of the space shuttle came two new spacesuits, the ACES or pumpkin suits worn by crew during launch and landing, and for work outside in the vacuum of space, the EMU, for Extravehicular Mobility Unit. The EMU is like a mini spacecraft. It provides self-contained life support for its wearer for more than 8 hours, and it was the suit in which astronauts learned in-space construction techniques during the early shuttle years. The design was commissioned by NASA in 1974, and although there have been many refinements, essentially the same EMU is still in service on the International Space Station. It was the EMU that enabled the construction of the orbiting laboratory. The suit has 14 different layers with a range of different functions, including insulation from extremes of temperature and protection from micrometeoroids. Pressure inside the suit is about 1/4 of standard atmospheric pressure. Higher suit pressures mean less mobility, but the low pressure means the astronaut must breathe pure oxygen. Nitrogen bubbles would condense in the wearer's bloodstream and body tissue if low-pressure air was used. In preparation for a spacewalk, an astronaut must pre-breathe pure oxygen for several hours to purge his system of nitrogen, and this process starts before the astronaut begins getting into his suit. The upper part of the suit is a rigid shell made from fiberglass. It provides firm attachment for the life support backpack and a toolkit mounted at the chest. As part of their preparation for a sojourn on the International Space Station, mission specialists will spend long hours training in the EMU at the Neutral Buoyancy Lab in Houston. Crew members have to be prepared for unexpected maintenance tasks outside the ISS. Problems with solar panels, coolant loops and leaky plumbing have required repair spacewalks. The Russian Orlan suit is also used on the ISS. It affords slightly less mobility than the EMU, but it is much quicker to put on, and its on-orbit maintenance is much simpler. The EMU was designed to be serviced on the ground, but ISS crews have had to adapt and learn how to open up the suit to locate problems and fix them. For complex repairs, ground specialists have even prepared video instructions for the ISS crew to follow.
Leak problem.
Every time the suit is put on, it is checked for leaks. While small losses are expected, any significant leak must be repaired immediately. Shuttle astronaut and physician Michael Barrett had to locate and replace a damaged O-ring. The failure of such a small part could threaten a whole mission. A new Z-series spacesuit is being developed, but evaluations will not be complete until at least 2020, so the familiar EMU will remain in service for a while yet. The 1970s vintage suit that built the ISS and kept the Hubble Space Telescope working deserves its big reputation. When a probe or satellite is launched, it can only perform its function because of a complex communications infrastructure here on Earth. A craft operating in deep space sends data via a transmitter with signal strength similar to a domestic light bulb. By the time it reaches Earth, a distance measured in millions of kilometres, this signal is incredibly weak. ESA, the European Space Agency, has 3 giant dishes at locations around the world, so it can communicate with its array of deep space probes. Cebreros is situated in a rural area west of the Spanish capital Madrid, where electromagnetic interference is at a minimum. The 35-metre dish is capable of fine pointing accuracy. Not only does the dish have to point directly at its distant target probe, it must track with it to compensate for both the probe's movement and the Earth's rotation. The 620-ton dish must move smoothly and with an accuracy of within 1 kilometre at a distance of 100 million kilometres. ESA's deep space dishes have to transmit as well as receive. For this, the power of the transmitter is important. A signal strength of 20,000 watts is focused into a narrow beam by the parabolic dish. The first antenna in ESA's deep space network was built at New Norcia in southwestern Australia. It's similar in design to Cebreros, the station which picks up signals from probes as the Earth's rotation takes them out of New Norcia's line of sight. Currently, the Deep Space Network has a heavy workload, as the Rosetta probe continues to transmit its own data and relay information from the Philae lander. The final member of ESA's deep space trio is Milagüe in Argentina, 1,200 kilometres west of Buenos Aires. This is the system's newest antenna, having been finished less than 2 years ago. It completes the network's coverage of the sky in any direction at any time. The 3 deep space dishes are coordinated from ESOC, the European Space Operations Centre in Darmstadt, Germany. In addition to the deep space probes, ESOC is also responsible for communication with Earth-orbiting satellites via a different group of smaller ground stations monitoring spacecraft in polar orbits. For more than 45 years, the Centre has provided the link between Earth and a variety of research spacecraft. Currently, the network is controlling 13 different long-term missions. Just getting it to the surface of Mars was difficult enough, yet the Curiosity rover continues to change our understanding of the red planet.
Okay, I'm out. Okay, he's out. He's close free. Okay, I put a little roll in, took it right out.
Gemini was NASA's hastily conceived bridging program, designed to perfect techniques needed for a lunar landing. Gemini 4 saw astronaut Ed White leave his capsule and walk in space, but the spacecraft's attempt to rendezvous with its booster had been a failure. Gemini 5 had set an American endurance record of close to 8 days, but its rendezvous exercise had failed as well. On the morning of October the 25th, 1965, 2 rockets stood awaiting launch at Cape Canaveral. While astronauts Wally Schirra and Tom Stafford prepared for blastoff on Gemini 6, a special Atlas Agena target vehicle stood waiting on Pad 14. Because rendezvous and docking was integral to its moon landing strategy, NASA had commissioned the Agena docking module. It would be carried to orbit atop an Atlas booster. As the Gemini 6 crew were being strapped in, the Atlas-Agena combination was entering the final minutes of its countdown. The plan was for Gemini 6 to rendezvous and dock with the Agena 4 times in a flight that was expected to last 2 days. Gemini 6 was scheduled to launch around 90 minutes after the Agena, with the countdowns being tightly synchronized. The target vehicle lifted off as planned. This was the first Agena flight as part of the Gemini program, but the Atlas booster had served well during the Mercury program, and the Air Force had had success with the Agena upper stage, so no problems were expected. Gemini 6 waited as the target vehicle accelerated after a perfect launch. But minutes later, as the upper stage separated, all telemetry was lost, and tracking radar detected 5 separate pieces. The Gemini mission was now pointless, and the launch was cancelled with Schirra and Stafford leaving their spacecraft. There was debate about what to do next. Scheduling for the Gemini program had been tight, with roughly 1 new launch every 6 weeks. There was no replacement Agena ready to launch before the next flight, Gemini 7. On the morning of December the 4th, 1965, astronauts Jim Lovell and Frank Borman were breakfasting before the launch of their Gemini 7 spacecraft. Among the others dining with them were the Gemini 6 crew, who would launch 9 days later. Gemini 7 was to be the longest duration flight yet, and for comfort during almost 14 days in orbit, the crew were wearing new lightweight spacesuits. NASA's doctors were worried about the effect prolonged exposure to weightlessness would have on astronauts, particularly the observed loss of red blood cells.
3, 2, 1.
Gemini 7 was designed to answer medical questions. It launched on schedule, before Gemini 6, which had been renamed Gemini 6A.
We're on our way, Frank.
It had taken NASA more than 60 days to prepare for a new launch. Now crews had 8 days till the launch of Gemini 6A, and they swung into action immediately. As soon as they reached orbit, the Gemini 7 crew turned their craft and began tracking with its upper stage. Gemini 4 attempted this, but had failed due to an insufficient knowledge of orbital mechanics. On December the 12th, Schirra and Stafford again prepared for launch. If all went well, within 6 hours of blastoff, they would be orbiting alongside Gemini 7. The launch pad crew had done an excellent job readying the booster in record time, and the countdown continued smoothly.
2, 1. Ignition. Shut down, Gemini 6.
But then shut down. The engines had started, and after 1 second, they stopped.
Oxidizer pressure is down to about 32.
The commander Schirra had the option of pulling the D-ring and ejecting both of them from the capsule, but he sat tight.
Just sitting here breathing.
Nobody knew what had gone wrong. For a second time, the crew of Gemini 6 had failed to launch. A connector had come away before the booster had lifted off, and the onboard computer closed everything down. This was rectified, along with another glitch in a turbo pump. 3 days later, they were ready to try again.
Go. 5, 4, 3, 2, 1.
The flight plan called for the rendezvous to happen on Gemini 6's 4th orbit, and Schirra made the first orbital correction 94 minutes into the flight. Gemini 7 would remain passive, with all orbital adjustments being made by Gemini 6. After 3 hours, slightly more than 400 kilometres separated the two craft, and Gemini 7 was picked up by Schirra and Stafford on radar. After 5 hours, Gemini 7 appeared as a bright dot, and soon after, the two spacecraft were flying in formation.
6 and 7 away, we'll be standing by if you have anything for us.
Okay.
3 years earlier, in 1962, the Russians had launched Vostoks 3 and 4 so that they could pass close to each other, and it had seemed like another Soviet triumph. With the rendezvous of Gemini 6 and 7, the Americans realised that the Vostoks had accomplished 2 well-timed launches, a very different achievement to the precision on-orbit changes they had accomplished. For more than 4 hours, the two spacecraft flew side by side, sometimes coming as close as 30 centimetres. It gave NASA confidence in its rendezvous technique, but there had not been a docking as had originally been intended when the target had been the Agena. After slightly more than a day in orbit, Gemini 6 re-entered the Earth's atmosphere and was picked up in the Atlantic Ocean. Gemini 7 continued on in orbit for 2 more record-breaking days, with Borman and Lovell reading books to pass the time. They returned to Earth on December the 18th, and were picked up by the Wasp, the same ship that had recovered the Gemini 6 crew. It was at this point that NASA started to believe the American space program was gaining greater expertise than their Soviet adversaries. However, the elusive docking exercise had still not taken place, and nobody realized just how difficult this would be. When the Cassini probe reached Saturn, staff at the JPL Operations Center watched eagerly for confirmation that it had carried out its orbital insertion instructions. It arrived in July 2004 after a journey lasting almost 7 years, and it had to perform a precisely aligned 95-minute burn to enter a highly eccentric orbit. Because of the great distances involved, the craft has to perform autonomously. Instructions to Cassini are sent a long time in advance via the Deep Space Network. Signals confirming that it had gone into orbit took 85 minutes to reach Earth. After 6 months orbiting Saturn, Cassini approached Titan, Saturn's biggest moon. By this stage, it had already flown past Titan several times, capturing radar and photographic images. This time, it released a lander, the Huygens probe. Titan is so large, it holds a thick atmosphere, so Huygens was equipped with a heat shield and a parachute. As it was floating down towards the surface, the lander began taking photographs and analysing the atmosphere's constituent gases. It made the first soft landing in the outer solar system, and although it performed well, relaying data back to Cassini, only one of the orbiter's recorders was on. Half of the images were lost. We now know that Titan has lakes on its surface, lakes of liquid methane. The Cassini probe has been active for more than 10 years, and during that time, it's helped us learn about the strange behaviour of Saturn. At first, it seemed that the northern and southern hemispheres of the gas giant were rotating at different rates, but it now appears that the wind speeds in the south are faster. Cassini's looping orbit is regularly modified so that it can pass close by features that mission specialists want to study. Another Saturnian moon, Enceladus, surprised observers. It is 1/10 the size of Titan, yet it appears to hold a thin atmosphere of water vapour. Observations suggest this atmosphere is being replenished by cold water volcanoes near the South Pole. Cassini is equipped with a mass spectrometer, and it was able to detect salt, water, and various hydrocarbons. It is now thought that a salty ocean lies beneath Enceladus's icy crust. Some planetary physicists believe Saturn's inner E-ring receives its particles from Enceladus. In 2008, Cassini was renamed the Equinox mission, and recently it received another extension and became the Cassini Solstice mission. It takes Saturn roughly 30 Earth years to orbit the Sun, and, like the Earth, its axis is tilted, so it has seasons. When Cassini arrived, the planet's North Pole was in shadow, and it was only recently that the probe could capture images of the peculiar hexagonal polar vortex. This hexagonal pattern was first observed in the 1980s by the Voyager mission. As spring in Saturn's northern hemisphere progressed, 2 giant storms were seen developing. They showed us hot spots in the infrared part of the spectrum, with both travelling towards the west. The larger storm moved faster, eventually engulfing the smaller one. Even after disturbances in the cloud patterns had dissipated, the storm still registered in the infrared. The rings orbit over Saturn's equator, extending from 6,000 to 120,000 kilometres above the surface, yet they are only 20 metres thick. They're made of ice, with particle sizes ranging from fine dust to 10-metre chunks. There are clumps within the rings that have changed since the Voyager's visits in the early 80s, with the inner F ring seeming to vary over a period of weeks. Saturn has at least 150 moons, and moonlets within the rings are thought to disturb the particles. Toward the end of its mission, with fuel running low, the risky trajectory will begin. Cassini will pass between the planet and its innermost ring, where the chance of collision with orbiting debris is extreme. It will sample the upper atmosphere and learn about the mass of the rings. To avoid possible contamination of the fragile moons, Cassini will ultimately be crashed into Saturn. In 2005, the Mars Reconnaissance Orbiter was headed to what were becoming the crowded skies above the Red Planet. Mars Global Surveyor, Mars Express and Mars Odyssey were in orbit around Mars, and the Spirit and Opportunity rovers were on the surface. But the MRO has a lot of different tasks, all paving the way for future Mars missions, and culminating in a manned landing on the Red Planet in about 15 years. It has been mapping Mars in fine detail, and this information has already been used to select a landing site for the Phoenix lander. The orbiter is also collecting detailed information about the weather patterns on Mars. While it continued to transmit a clearer picture of the planet, back on Earth, a new rover was taking shape. A rover like none before, and one that would work very closely with the MRO. Lockheed Martin, under the supervision of NASA's Jet Propulsion Laboratory, was building a rover the size of a small car. Unlike previous rovers, it wouldn't use solar panels for its power. It's equipped with a radioisotope thermoelectric generator with a minimum lifespan of 14 years. Known as Curiosity, the rover has a range of cameras and chemical analysis tools, as well as a robotic arm and radiation detector. Before it could fly, Curiosity had to be tested at extreme temperatures and vibration. Towards the end of 2011, Curiosity, fixed into its entry, descent and landing module, was packed into the nose cone of an Atlas V. Because of the proximity of Mars, the launch window was extremely narrow.
3, 2, 1. Main engine start, 0, and liftoff.
It would take the craft more than 8 months to reach Mars. The Centaur upper stage pushed the craft out of Earth orbit onto a trans-Mars trajectory. Before they separated, the Curiosity package was set rotating for stability. The crew's assembly was equipped with heaters to maintain stable temperatures for critical subsystems that remained dormant during the cruise phase. Solar cells provide power for communication with mission control, and thrusters are used for course corrections.
Things are looking good. Coming up on entry.
As it approached Mars, the team at NASA's Jet Propulsion Laboratory waited. 10 minutes before reaching Mars's atmosphere, the cruise stage was jettisoned, and an incredibly complex sequence of events was about to unfold. As it entered the atmosphere, it was travelling at about 20,000 kilometres per hour, and the first stage of deceleration began. thrusters kept the craft aligned to the target, selected with the help of the MRO. Signals confirming each stage of the descent were relayed back to JPL via the Mars Odyssey. Next, balance weights were thrown off, so the craft could keep the correct attitude for parachute deployment. Still moving at 1,600 kilometers per hour, the small parachute unfurled, and the heat shield was discarded. From orbit, the MRO captured this image of the descent stage. At 1,500 meters, the descent stage separated from the back shell, and the landing thrusters ignited. A radar altimeter monitored both the craft's height and its speed. At a height of 20 meters and now moving at 3 kilometers per hour, the rover was lowered on cables and the wheels deployed. When it was on firm ground, it fired pyros, severing the cables. The sky crane technique was used so that dust and debris stirred up by the rockets couldn't damage the rover.
Touchdown confirmed. We're safe on Mars.
Most of these JPL people have devoted large parts of their lives to this project. This was the first time such a landing had been attempted, and it had been flawless. Almost immediately, an image was relayed back. Using one of its hazard avoidance cameras, Curiosity had sent an image of the surface, and the Mars Reconnaissance Orbiter was playing a vital role as a communications hub. It records signals sent via the rover's UHF transmitter and retransmits them when it can see Earth. Curiosity had been set down near the Gale crater, just south of the Martian equator. Initially, the rover began transmitting detailed information about its system status and its descent and landing experience. During its first days on Mars, the rover's now redundant flight program was dumped and replaced with surface operations software. Its camera mast was extended, and Curiosity began changing completely the way we think about Mars.
Beautiful valley.
Really amazing.
The Earth's magnetic field is weakening, and the magnetic poles are drifting. The constellation of swarm satellites is attempting to find out what's happening at the molten core of our planet.
Gemini 7, are you able to see in the windows of 6 very easily and vice versa?
The combined Gemini 6 and 7 missions had flown in formation, but an original objective for two craft to join together in orbit, a process known as docking, could not be attempted because Gemini 6's Agena target vehicle had exploded just after launch.
We can very clearly see the horizon scanners operating.
All remaining Gemini missions would include rendezvous and docking, and Gemini 8, with first-time astronauts Neil Armstrong and Dave Scott, would be next. All NASA astronauts must be qualified pilots, and the space agency operates its own wing of T-38 jet trainers. To keep their flying hours up, astronauts often fly themselves between facilities across the United States in one of these two-seaters. Elliot C. and Charles Bassett, the astronauts slated to fly Gemini 9, died in poor weather conditions when their T-38 crashed into a building at the McDonnell Aircraft Plant in St. Louis. They were going to inspect their spacecraft. Gemini 9 would become Tom Stafford and Gene Cernan's mission. Each flight had a backup crew that could take over at short notice. NASA was still in a hurry. On March the 16th, 1966, Gemini 8 waited on launch pad 19, while an Agena target vehicle waited on pad 14. The Agena would launch 95 minutes before the Gemini craft, and the two would dock about 6 hours after launch. But docking was not the only aim of the Gemini 8 mission. Dave Scott was due to make America's second spacewalk. There had been setbacks in the Gemini program, and this flight was aimed at catching up. As Armstrong and Scott were being strapped into their craft, the Agena was in the final seconds of its countdown.
2, 1, 0.
Mission controllers' faith in the Agena had been shaken after the previous vehicle had blown up at the ignition of the second stage. But soon after its launch, there was confirmation that this Agena would be waiting correctly in orbit when Gemini 8 arrived. The Agena was supposed to be controllable from the ground or from the spacecraft, but because there had been difficulty in receiving information from the target craft, Mission Control still had doubts about the Agena's attitude control system. Prior to docking, the crew were warned to turn the Agena's system off if it gave trouble. The docking manoeuvre went so smoothly that ground crew were at first uncertain that it had really happened. But soon there were problems as the linked craft began spinning and not responding to control. Immediately, Armstrong undocked, but the spin got worse with the astronauts in danger of passing out. They initiated an emergency return to Earth. Later analysis exonerated the Agena, revealing that one of the Gemini craft's thrusters had remained stuck on. The flight had lasted less than 11 hours. The two craft had only stayed docked for 30 minutes, and there had been no spacewalk. Yet mission planners noted the calm and professional way that Armstrong had handled what could have been a tragedy. Armstrong and Scott splashed down in the Pacific near Japan, the only Gemini craft not to land in the Atlantic. After the failure of the Atlas Agena target vehicle for the original Gemini 6 mission, its makers were relieved that it had performed well for the Gemini 8 mission. Some said difficulties had been due to the mix of different companies building the thing, with Convair making the Atlas first stage, Lockheed making the upper Agena stage, and McDonnell responsible for the docking adapter. In May 1966, GATV-9 was prepared for launch. It would be Gemini 9's docking target. The first 2 minutes went perfectly, but after that, a short caused the right booster engine to gimbal hard over. The rocket flipped and headed back toward the ocean where it crashed. Convair accepted responsibility. As with Gemini 6, this left 2 astronauts sitting in a fully fueled Titan with nowhere to go. Tom Stafford, who'd been involved in 2 on-pad aborts with Gemini 6, and now this with Gemini 9, was nicknamed the Mayor of Pad 19. But this time a standby docking vehicle was available. The upper stage had no propulsion, but it did have a docking collar. It launched 2 weeks later. Gemini 9, now renamed Gemini 9A, was to follow shortly. But 3 minutes before the scheduled blastoff, ground computers lost contact with the Gemini computers. With only a 40-second window, the launch was scrubbed. Two days later, they tried again. This would be the 6th time Commander Stafford had been strapped in, with only 1 mission completed. Stafford and Cernan quickly caught up with their orbiting target, but something else had gone wrong.
Looks like an angry alligator out here rotating around.
The protective shroud had not come away. Inexperienced technicians had taped down the fiberglass lanyards, and they kept the 2 pieces together. Stafford dubbed it the angry alligator. Engineers on the ground desperately sought a solution, but there was just too much risk to the astronauts. There would be no docking on this mission. Next, Cernan left the capsule. He was to test a new manoeuvring unit, but his heart rate rose so alarmingly that the doctors ordered him back inside. He was overheating and his helmet had fogged. John Young would command the next mission, Gemini 10. His partner would be Michael Collins, making his first flight. He was also due to make the next spacewalk and was training in a cradle floating on air. This was to give him practice using the zip gun, but so far the spacewalks were presenting unexpected difficulties due to overexertion. This looked relaxing.
2, 1.
The Gemini flights were starting to conform to a pattern, with an Agena target vehicle launching 100 minutes before the manned spacecraft. This time there were no launch delays. The astronauts had a busy schedule, having to make up for the shortcomings of the 2 previous flights. The Agena was waiting for them exactly as intended. Rendezvous was now becoming routine. Young and Collins caught up with it, and after almost 6 hours they had docked. Gemini 10 used an 80-second burst from the Agena's engine to boost them to a higher orbit, where they visited an Agena from the Gemini 8 flight. Their rendezvous and docking exercises had gone well, but activity outside the spacecraft had still been difficult, with the inflated spacesuit limiting movement and important equipment being lost. On the following Gemini 11 flight, Richard Gordon also had great difficulty performing effectively outside the craft. NASA came up with a new training technique, one that they use to this day. Scuba diving had been seen as good training for fitness and regular breathing. Now they'd built a mock-up of the Gemini-Agena combination in a high school swimming pool in Baltimore. With just 60 days before Gemini 12, Buzz Aldrin began practicing his scheduled routine. In addition to his spacesuit, he carried 28 kilograms of lead to give him a neutral buoyancy. A clip-on tether was designed to solve the problem that previous astronauts had had just staying in one place. Detailed feedback from Aldrin helped engineers position handholds to make extravehicular activity, EVA, more precise. November the 11th, 1966, and the pad crew were all there for the final Gemini mission. Commander James Lovell and his pilot Buzz Aldrin arrived at their rocket with placards on their backs saying, "The End." Many of the team wishing them farewell had spent years on this project. There had been a suggestion that Gemini 12 should be delayed to coincide with the first launch in the Apollo series, but delays with the new spacecraft and its giant booster made this unfeasible. Rendezvous with the Agena was as expected, but on the ground, an anomaly in telemetry data suggested that the Agena's main engine could give problems, so they cancelled the boost to a higher orbit as had been intended.
Okay.
Lovell docked the two craft. The next day, when Aldrin opened the hatch and moved outside, everything was different. The handrails made an immense difference. The gradual and deliberate way Aldrin moved gave no problems with exertion or overheating. He easily completed all his tasks, including attaching a tether between the Gemini and the Agena. When the spacecraft undocked, they remained connected. This is a technique NASA wanted to test, but it has not been used since. Project Gemini had ended on a high note. Jim Lovell had set a new record for the most hours in space, and his pilot, Buzz Aldrin, had more EVA hours than anyone else. The Gemini missions had achieved all they had set out to do. But ahead, there was an even bigger goal, and a much bigger rocket was being developed to make it happen. Nobody realised just how difficult the next stage would be. August the 6th, 2012, and NASA's Curiosity rover is safely on the surface of Mars. Early weeks were devoted to reprogramming the rover and calibrating its suite of instruments. The rover had landed in Gale Crater, a scar left after a meteor impact more than 3 billion years ago. Gale Crater had been chosen because it shows signs that water had once been present. Curiosity is focused on water and its effect on the early years of the red planet, particularly whether it could have supported life. The rover is fitted with a number of specialist cameras. On the central mast are 2 cameras that provide images in true colour, and their sensitivity extends beyond the visual spectrum. One camera has a 15-degree field of view, while the other provides a narrower 5-degree view. Both have 8 GB of flash memory. Curiosity has 2 computers. They coordinate the radio transmissions back to Earth, either directly via the X-band transmitter or with UHF via the Mars orbiters. Relay via the orbiters is preferable as it gives a higher data rate. Also on the rover's mast are 2 black and white navigation cameras designed to deliver a 3D view for ground crew plotting the path the rover will take. Curiosity's first major destination was Mount Sharp, rising 5,500 metres above the crater floor. But it took around 2 years to get there, as the terrain is littered with features that the planetary investigators want to examine. The rover is capable of navigating autonomously, but it still relies on instructions from NASA's Jet Propulsion Laboratory to set short-range destinations. The images, backed up by chemical analysis, show unequivocally that water was once present at this site. Also housed in Curiosity's mast is a laser that works in conjunction with a suite of instruments known as ChemCam. From as far as 7 metres, it can vaporise a tiny sample and analyse its chemical composition. If a rock bears closer examination, a drill at the end of the rover's robotic arm can extract a sample. The arm also has an X-ray spectrometer and an imager able to capture pictures down to microscopic detail. Powder extracted from the rock is poured into the aperture of the ChemMin instrument. Using X-rays, the instrument can identify the mineral content of the rock. The first samples that Curiosity tested revealed sulfur, nitrogen, hydrogen, oxygen, phosphorus and carbon. Yet there have been problems. Just months into its mission, the primary computer went into safe mode. Using the backup computer, it took JPL staff 3 days to restore the system. And Curiosity's light metal wheels are starting to show signs of damage. Some of the rocks are both so jagged and firmly fixed into the Martian soil that the rover drivers are having to think more carefully about the paths they select. The rover has 2 radiation detectors, and information from these suggests that a manned mission to the Red Planet would not be unduly troubled by excessive levels of radiation. The next phase of Curiosity's assignment will see it climb the slopes of Mount Sharp. Mission specialists are excited about the different strata of rock they expect to find. A stream of charged particles emanates from the Sun. Known as the solar wind, it flows throughout the solar system. During extreme solar activity, coronal mass ejections bombard the planets. The Earth is largely protected by its magnetic field, but at polar regions, where the magnetic field lines converge, charged particles can spiral down and interact with the upper atmosphere, manifesting as auroras. We know from the Earth's geological record that the poles flip unpredictably from between 100,000 to 50 million years, and over the past 150 years, the Earth's magnetic field has declined in intensity by about 15%. To find out more about our planet's fluctuating magnetic field, the European Space Agency launched a trio of magnetic observation satellites known as SWARM. The 3 identical satellites measure both the strength and direction of the Earth's magnetic field as it continues to evolve. An hour after launch, they each deployed a magnetometer positioned at the end of a boom to isolate it from any stray fields generated by the satellite's electronics. Called Alpha, Bravo and Charlie, the trio were accurately delivered to north-south orbits at a height of 490 kilometres. The oscillations of the boom would take several minutes to stabilise. Over time, Alpha and Charlie will follow the same path, and their orbits will be allowed to decay. Bravo will maintain its launch altitude, but it's gradually drifting to a different orbital plane. This will allow researchers to gain a 3-dimensional view of the magnetosphere. Though most of the Earth's magnetic field is generated by movement within the molten iron core, some magnetism is retained in areas of rock, and saltwater currents in the oceans also contribute. The swarm satellites will enable researchers to build a dynamic map of the planet's interior. They want to understand why the magnetic field is diminishing and why the Earth's magnetic poles are drifting. 780,000 years ago, the magnetic poles flipped, and researchers want to know whether the present fluctuations are symptoms of the approach of another field reversal. A weak area in the magnetosphere above the South Atlantic allows the solar wind to penetrate to lower altitudes. More satellites fail passing above this region than at any other place. The knowledge gained from SWARM has implications beyond sensitive electronics. Continued weakening of the magnetic field will allow more solar radiation to reach the Earth's surface, with implications for all living things. The European Space Agency has been sending astronauts deep underground as training for extended stays on the International Space Station. In the early 60s, during the Mercury program, the United States began developing a giant booster capable of carrying a crew of 3 to the moon. It used a cluster of tanks originally designed for other rockets, and the first flights just tested a mammoth lower stage. It became known as the Saturn I. Launches began in 1961, but although it could lift heavy loads, without upper stages it could not reach orbit. Engineers were expecting the usual teething problems with the big new rocket, but there were none. Every launch went as planned. At the same time, the new, much larger Apollo spacecraft was being developed. The initial Block 1 version was designed when NASA still envisioned the capsule with a large descent and return module would land directly on the moon. Several of these early models were built as test articles before NASA settled on a modified Block 2 design that included a docking probe and would work in conjunction with a lunar landing craft. Like previous American spacecraft, the Apollo capsule was designed to land in the ocean. Every situation was rigorously tested, and sometimes the value of these tests was glaringly obvious. The Apollo capsule was fitted with an escape tower, like its Mercury predecessor. In an emergency, sensors would trigger the solid fuel rockets, which would pull the craft away from an exploding booster. This was tested from a specially designed Little Joe rocket. During tests in 1965, the Little Joe was meant to test a high altitude abort, but just 26 seconds into the flight, the rocket developed a roll. It was a genuine emergency, and the system had worked perfectly. All across the US, different Apollo subsystems were being tested simultaneously. Though NASA now felt it had achieved parity with Russian technical ability, it was still in a race to the moon, still focused on President Kennedy's end of the decade deadline. was a masterly feat of organisation. NASA enjoyed generous funding and popular support, with the United States going through a space-led technical revolution, and astronauts rivaling movie stars as figures of public adulation. By February 1966, a Saturn 1B was ready for an unmanned all-up test. This was a new technique for NASA. All-up testing meant testing a range of new systems in the one flight.
6, 5,
if all went well, it would save a lot of time.
Sequence start. 1, 0, launch commit. We have a liftoff. All engines building up thrust. Moving out.
The Saturn I lower stage had been improved and was now known as the S-1B. This time there was a second stage, the S-4B. The combination would lift a Block 1 version of the Apollo spacecraft for its first flight. The capsule splashed down in the Atlantic 37 minutes after launch. The mission was generally a success, though there were engine difficulties, and wiring problems led to a loss of steering control and distortions in telemetry data. The focus now shifted to the first manned flight. Gus Grissom, one of the original Mercury 7 astronauts, Ed White, the first American to walk in space, and first-timer Roger Chaffee would crew an old-style Block 1 Apollo capsule in a mission scheduled for February 1967. Grissom had done valuable work in the development of the Gemini spacecraft, and he'd commanded the first Gemini mission. He'd taken on a similar role with the new Apollo command module, but he was becoming frustrated. He was concerned about the lag between changes made to the command module and the corresponding alterations to the simulators. The amount of flammable material that was in the crew compartment was also raised several times. While the booster technology was progressing steadily, the sheer complexity of the spacecraft was seeing it slip behind schedule. NASA was finding numerous deficiencies with the quality delivered by contractor North American Aviation. Another aspect of the astronauts' work involved an ever-expanding commitment to the mass media. Since its inception, NASA had decided that its activities would all be open to public scrutiny, in contrast to America's Cold War adversary, the Soviet Union, which chose to shroud its space program in secrecy. NASA's Public Affairs Office employed journalists who understood what working journalists needed, yet it was clear that the astronauts found photo calls a distraction. Regular press days were held in the lead-up to the mission. As the launch day approached, training in simulators shifted to testing of the spacecraft itself, sometimes in a vacuum chamber and sometimes as it sat atop its booster. One of these procedures, known as a plugs-out test, was to evaluate the Apollo capsule's function while it was disconnected from launch control, operating independently on its own power. There was no fuel in the spacecraft or in the booster, and all the pyros and explosive bolts were disabled, so this was regarded as a very safe situation. All other parameters would be the same as in a live countdown and launch. The astronauts would breathe pure oxygen at slightly above atmospheric pressure. This early version of the capsule had an old-style hatch that opened inwards. It would be held in place by the internal pressure. Later manned missions would have a different outward opening hatch. For hours, the simulated countdown stopped and restarted, but at 6:30, a spark triggered a flash fire. In the pure oxygen environment, it consumed the capsule, killing the 3 astronauts in seconds. The United States was in mourning. Gus Grissom, Ed White and Roger Chaffee were buried with full military honours. Many at NASA had been dreading this kind of outcome, In a speech to colleagues at Mission Control, Flight Director Gene Kranz said, "We were too gung-ho about the schedule, and we locked out all of the problems we saw each day in our work." Manned flights were suspended. The space agency had to find out what went wrong and then completely redesign the capsule and mission procedures. All Apollo remnants were impounded, and NASA initiated an exhaustive investigation. Both houses of Congress also set up inquiries. Frank Borman was the only astronaut to serve on NASA's Accident Review Board. He was one of the few astronauts to serve as commander on his first mission, Gemini 7, and he'd been selected to command the third manned Apollo mission, but there was a cloud over the whole program. Ultimately, Borman's testimony before a House committee helped convince Congress that the manned Apollo program was safe to resume operations. Outside the inquiries, NASA tried to maintain its focus. Astronauts who were experts in every aspect of flight and related engineering were now being sent on field trips to learn about geology in preparation for moon missions. Although manned missions for 1967 had been put on hold, NASA still scheduled flights. The giant Saturn V booster, needed to get to the moon, was finally ready for launch. There had been delays with the second stage. Apollo 4 would be another all-up test, which included the problematic command module. On delivery from contractor North American Aviation, it was subjected to close scrutiny. More than 1,400 problems were discovered. The response of NASA managers, who were close to the Apollo 1 astronauts, ranged from fury to tears. Remedial work on the command module took 4 months, with Apollo 4 finally ready for launch in November 1967. The new rocket was covered in sensors, and cameras would record critical
Ignition
functions.
sequence starts. 5, 4, we have ignition. All engines are running. We have liftoff. We have liftoff at 7 a.m. Eastern Standard Time.
My God, our building's shaking here. Our building's shaking. The floor is terrific. The building's shaking. This big glass window is shaking. We're holding it with our hands. Look at that rocket go into the clouds at 3,000 feet.
The cameras, intended to monitor the intricacies of staging, captured some of the most iconic images of the Apollo program. They were jettisoned soon after these pictures were captured and parachuted back for an ocean recovery. At this point, nobody knew whether President Kennedy's goal of a lunar landing by the end of the decade was achievable, and the Apollo 1 tragedy was making a lot of Americans have second thoughts about the race to the moon. Working on the International Space Station involves very specific scientific tasks, in combination with having to deal with the unexpected. And although ground control will provide advice, astronauts must be resourceful and good at solving problems. Space is a hostile environment, and their lives could depend on it. As part of its astronauts' training, ESA runs a regular caves exercise, where astronauts from across the ISS's partner agencies come to work together in Sardinia's Sagruta cave system. ESA has been running CAVES for 8 years. It's a convoluted acronym of Cooperative Adventure for Valuing and Exercising Human Behaviour and Performance Skills. The lack of a day-night cycle, sensory deprivation, claustrophobic spaces and an absolute need for good teamwork provide a strong analogue with spaceflight. Each new group meets for a training program that is also a multicultural team-building exercise. Experienced cavers brief the astronauts on what they can expect. This team will spend 6 days in the caves, though previous expeditions have been underground for as long as 2 weeks. The caves training is not just an endurance test. The team is expected to do some serious research. Last year's group discovered a new species of crustacean within the caves. The participants also learned 3D mapping skills and are expected to survey 1.5 kilometres of the largely unmapped Sagruta system. Before their long underground expedition, the astronauts visit several small caves to familiarise themselves with the routines. In orbit, they are the arms and legs of the extended science team on the ground, and a similar plan is followed here. The group will be measuring carbon dioxide and radon levels, as well as taking microbiological samples. These detailed scientific measurements are carried out according to strict guidelines. On the first day of the expedition, the astronauts say goodbye to the usual pattern of day and night. For the next 6 days, the only light they will have will be from their headlamps. Though they will still follow a daily routine, there are no visual clues to the passing of time. Each team member carries 2 short tethers at his waist. Safety protocols, similar to spacewalking, require these to be used in all dangerous situations. Discovered in 1950, the Sagruta cave system includes both dry and wet caves. Humidity levels throughout the system are uniformly high, and year-round the temperature remains at 14 degrees. The team spend several hours making their way to a central gallery where they set up a base camp that will serve as their centre of operations. Tents are necessary because of the constant dripping. The ready availability of water makes this a good campsite. Here, the technical instructors delegate all planning and decision-making authority to the team's elected leader. The daily routine is organised around timelines. Just like teams on the International Space Station, every day's activity is planned in advance. The group explored 2 branches of the cave system, going past an area named Lake Baikal and continuing on into galleries that had not been seen before. They were looking for a forward campsite, but could find nowhere suitable. The next day, the team donned their wetsuits. They would explore a riverine area mapped by the previous expedition. Since a test course in 2008, more and more situations similar to spaceflight have been introduced underground. Though the physical demands placed on the astronauts are not extreme, they are under stress. The lack of light makes movement and equipment handling more difficult, and the absence of a day-night cycle distorts the perception of time. ESA believes the cave environment provides an exceptional training for long-duration spaceflight. At a cavern called the Ballroom, the group have reached the limits of the map. they press on into an uncharted region where they discover 2 huge new galleries. Just as in space, making an accurate photographic record is an important part of the documentation. They decide they'd like to establish a forward camp here, but before they can, mission protocols say they must inform cave control. Making radio contact through more than 100 metres of solid rock is impossible, but they have a type of digital telephone that transmits using the conductivity of the wet ground. The group spend 2 more days in the area recording the insect population, taking water and air samples and mapping the galleries. Finally, it was back to the surface, where hot showers and cooked meals were waiting. But before they return home, the final phase of the operation has to be completed. All the research work must be written up and presented.
Allumage Vulcain. Allumage des EAP.
May the 14th, 2009, and an Ariane 5 launches the Herschel Infrared Telescope and the Planck Space Observatory. Planck was headed to a Lagrangian orbit around a point 1.5 million kilometres beyond the Earth. Its job was to map variations in the cosmic microwave background, or CMB, the remaining echoes of the Big Bang at the beginning of the universe. To do this, it had to be sensitive to differences in temperature across the sky, down to millionths of a degree. While it was operational, its detectors had to be refrigerated to 1/10 of a degree above absolute zero, making it the coldest object in space. As it scanned the skies, it slewed with a high degree of precision, enabling it to make a 3-dimensional map of the universe across 9 different wavelengths. When the CMB was first observed in 1965, it was seen as uniform in every direction. Instruments that could detect its minute variations did not exist. Images formed from different wavelengths give clues to the formation of the galaxies, and data from Planck has changed cosmologists' ideas about early star formation. Evidence now suggests the first stars ignited 140 million years later than had previously been thought. As the early universe cooled, light flooded the skies. As the universe continued to expand, this light faded, yet the CMB persists, providing an image of the universe in its infancy. Not only is the accuracy of information from Planck allowing cosmologists to recalibrate the timeline of the universe, it's prompting revision of the theory of inflation that doesn't fit the picture revealed by the probe. Planck was decommissioned in October 2013, when the depletion of its helium coolant rendered it inoperable.
Really amazing.
Testing technology in zero gravity, lunar gravity, or even Martian gravity. Techniques pioneered for the early space program find widespread uses in modern research. At the beginning of 1968, NASA was preparing to launch the unmanned Apollo 5. A Saturn 1B would lift a very different payload to low Earth orbit. It had been 12 months since 3 astronauts were incinerated, preparing for the Apollo 1 launch. Supporters of the American space program feared that inquiries in both houses of Congress, set up after the tragedy, would axe the Apollo program. But President Lyndon Johnson, who had decorated 2 of the Apollo 1 astronauts, had influence on Capitol Hill, and his ongoing support for NASA helped quell any political backlash. Work on a redesigned Apollo capsule was progressing. But the rush to meet President Kennedy's end-of-the-decade deadline sat uncomfortably with the need for precision and quality. All flammable materials had been eliminated from the spacecraft and spacesuits. At launch, the astronauts would no longer breathe pure oxygen, and the complex hatch had been replaced by a one-piece unit that could be opened rapidly. More than 1,400 wiring problems had been corrected. But there was one vital piece of the Apollo program that remained untested. Nothing like it had ever flown. The lunar landing craft, known as the lunar module, had been plagued with development problems, and its first test flight had been delayed by almost 12 months. It consisted of a descent stage that would remain on the Moon and an ascent stage that would return the astronauts to the Apollo command module, waiting in lunar orbit. Each part had its own engine. In testing, the descent engine had not been burning smoothly. Of all the Apollo hardware, this engine had to respond to the most delicate control. Rigorous testing finally solved this problem, and LM-1 was prepared for flight. The unmanned Apollo 5 would test the craft in Earth orbit. The lunar module, packed beneath the unique nose cone, had no landing legs, as these would have further delayed delivery. And after pressure tests on LM-5 had blown out a window, LM-1 had aluminium panels instead of glass in its windows.
RTC, will you site select? Guido.
On January the 22nd, 1968, the 2-stage Saturn 1B stood fueled and waiting on Cape Canaveral pad 37B.
7, 6, 5, 4, 3, ignition detected.
Transmit 5 enter. Clock and start. 5 enter. Thrust okay. Affirmative. Program 11. Okay, TLK P11. Roll pitch start. Roll in pitch.
This mission would be judged entirely on telemetry, on the electronic flow from sensors monitoring every system in the booster and the lunar module. At the end of the flight, nothing would return to Earth.
Cutoff plus 50.
NASA needed to know how the lunar module's descent and ascent engines would function in space. A software problem shut down a descent engine burn after only 4 seconds, but Mission Control were able to reprogram it. After 11 hours, all systems had been checked, and the mission declared a success. Astronauts would only have one opportunity to fly the craft, and 2 different types of simulator were developed for training. The Lunar Landing Research Facility at Langley exposed astronauts to the kind of decisions they would have to make during the last 50 meters of their descent to the lunar surface. But this was a bit like a carnival ride, and the astronauts preferred the free-flying simulator known as the Lunar Landing Research Vehicle, or LLRV. It was nicknamed the Flying Bedstead. A gimbal jet engine provided partial lift that helped the craft behave as though it was under the influence of lunar gravity. The rest of the lift and the control came from throttleable rockets, similar to those in the lunar module. Just like any other aircraft, it had to be thoroughly tested, and NASA test pilot Joe Walker made the first series of flights in 1964. It could take off and fly using the jet engine and then be switched to sim mode when it would behave like the lunar module. In 1967, Neil Armstrong was the first astronaut to fly the prototype. The following year he flew a modified version with cockpit walls that limited his view to something like he'd see through the lunar module window. When switched into sim mode, the response to pilot control became sluggish, as close as experts could make it to the way the lunar module would behave in lunar gravity. Later, astronauts would call the LLRV the unsung hero of the Apollo program, but NASA administrators were having second thoughts. It would not be the last crash. Of 5 LLRVs and its derivatives, only one was left at the end of the Apollo program. The second Saturn V launch was the final unmanned Apollo mission, Apollo 6. Mission objectives included monitoring the amount of vibration a fully loaded Saturn V would experience. It was carrying a dummy lunar module and a hybrid command and service module. Like Apollo 4, it was not just covered with sensors, but cameras too. Being the first time the Saturn V was carrying a full load, engineers were keen to see how it performed. There were problems. Two minutes into the flight, vibrations ran through the length of the rocket, causing damage to the adapter housing the lunar module. When the second stage took over, 2 of its engines cut out early, affecting the final orbit. The third stage had to burn longer to compensate. Inside the command module, a camera was trained on the window and at various parts of the astronaut's instrument panel. After 3 orbits, the upper stage failed to reignite as commanded. NASA wanted to test the capsule in a high-altitude, high-speed re-entry, so the command and service module separated from the upper stage and used its own engine to boost it to a higher orbit for a faster re-entry. Though Apollo 6 was troubled with technical difficulties, NASA understood the vibration problems well and was able to redesign various subsystems according to the information gathered during this mission. Finally, NASA was ready to launch another manned mission, and by October 1968, Apollo 7 stood ready for launch. It had a completely redesigned command module, and the astronauts would wear a completely new spacesuit. After the Apollo 1 fire, the new A7L suit was fire-resistant with an outer layer of Teflon-coated beta fabric. A one-piece fishbowl helmet that did away with the need for a visor and a visor seal was fitted to the shoulders, allowing head movement and providing superior visibility. On the morning of October the 11th, 1968, 3 astronauts were prepared for the Apollo program's first manned flight. It would be the program's last Saturn 1B mission and would not carry a lunar module. Veteran of the Mercury and Gemini programs Wally Schirra and 2 first-time astronauts, Don Isley and Walter Cunningham, would be NASA's first astronauts to fly in almost 2 years.
4, 3, 2, we have ignition. Commit liftoff. We have liftoff. This is launch control. We have cleared the tower.
Roger, tower clear. 12 seconds out and the roll program has commenced.
The bigger Apollo capsule provided a more comfortable environment necessary for long-duration flights that were required to get to the moon. The crew could take off or put on their bulky spacesuits as required, and they didn't have to remain in their couches, as in the Mercury and Gemini spacecraft. Soon after reaching orbit, the command and service module separated from the S-4B upper stage. On a moon mission, this would normally house the lunar module. One of the 4 adapter panels had not opened fully. On subsequent flights, these would separate completely from the upper stage. The spacecraft turned around and practiced docking using a visual reference target that would usually be mounted on the lunar module. Not long into the mission, Schirra came down with a cold, and in the confines of the capsule, it quickly spread to the other 2. In zero gravity, the nasal congestion was not clearing in the same way it would on Earth, and the crew were very uncomfortable. Eating became a sore point with the astronauts. Though the food had improved since the earlier space missions, the freeze-dried and bite-sized rehydratable meals fell short of what they considered acceptable. The demands on this mission were considerable. Tense interchanges between the sick astronauts and mission control were not uncommon. They had to fire the service module engine no less than 8 times. Public relations reached new heights on the mission. A series of TV broadcasts from the capsule were watched around the world. At one point, Schirra refused to switch on the TV equipment because the schedule was too crowded and the crew had not eaten. Preparing for re-entry, a new dispute broke out. The astronauts refused to wear their helmets during the return to Earth. With their colds, they worried about the rapid changes in pressure. They wanted to hold their noses and blow to equalize the pressure. Aboard the carrier Essex, the Apollo 7 astronauts were treated as returning heroes. But they did not receive the usual NASA honours, and Schirra, Isley and Cunningham never flew again. Carbon dioxide is a small but vital component of our planet's atmosphere. The carbon that makes up the vast bulk of plant matter is extracted from this atmospheric CO2. In turn, the plants replenish the atmosphere's oxygen. All animal life breathes this oxygen and exhales CO2. This is called the carbon cycle. Our modern industrial societies rely on oxygen as well, and by burning coal and petroleum products, we produce the energy that powers our affluent lifestyles. This process produces carbon dioxide too. There has been a measurable increase in atmospheric CO2 since formal monitoring commenced. Higher levels of CO2 mean that the planet's blanket of air lets less of the Earth's heat escape out into space, prompting a slight rise in the planet's temperature. This has led to visible reductions in the Arctic sea ice and in the retreat of glaciers at the edges of the Antarctic continent. Using weather readings from around the world, NASA's Goddard Institute for Space Studies says that 2014 was the hottest year since 1880. The Goddard report revealed that 9 of the 10 hottest years on record have all been in this century. To understand the geographic distribution of the sources of CO2 and the regions that remove it from the air, NASA commissioned a satellite equipped with an extremely accurate suite of spectrometers to analyse the intensity of CO2 concentrations in the atmosphere. This was the second time NASA had built an orbiting carbon observatory. The initial satellite, OCO, launched in 2009, failed to reach orbit when the payload fairing didn't separate from the spacecraft and it could not achieve orbit. A duplicate orbiting carbon observatory, known as OCO2, successfully went into polar orbit in July 2014. Its north-south orbit allows it to overfly every point on the Earth's surface at least once every 16 days. It makes measurements in 3 different modes. Nadir mode samples the atmosphere directly below it, giving a global picture of the swirling concentrations of CO2. This map from Goddard was compiled using ground-based measurements. Data from OCO2 will deliver far greater detail. A second type of operation, target mode, enables the observatory to focus on a single point of interest, allowing it to gather multiple readings which can be compared with ground measurements made at the same site. The third, glint mode, sees the satellite sample close to the point on the Earth's surface that directly reflects the sun's rays. This further enhances the spectrometer's sensitivity, especially when sampling over the oceans. And OCO2 can detect oxygen concentrations, which will give a clear indication of the growth rates of plants and their ability to act as carbon sinks. OCO2 will remain operational for at least 2 years. In the early 1950s, NASA's predecessor, the National Advisory Committee for Aeronautics, carried out in-flight zero-gravity tests. By flying in a parabolic arc, an aircraft could offset the force of gravity for a short time. Early tests in a Lockheed XP-80 were rudimentary. Flying the precise parabola to maximise the zero-G time was difficult for pilots. It's hard to know what they learned from this kitten experiment. By 1959, at the commencement of NASA's Mercury program, parabolic flight was well understood, and it became a fundamental part of astronaut training. To achieve the effect, the plane climbs at a 45-degree angle. As the thrust is reduced and the aircraft's nose drops, passengers experience weightlessness until the plane's nose reaches a downward angle of 30 degrees when the pilot pulls out of the dive. In the mid-1960s, NASA employed 2 KC-135 aircraft for zero-G training. These are the military version of the Boeing 707. They were nicknamed the Weightless Wonders. During the Gemini program, astronauts were now required to walk in space, and the zero-gravity training flights came into their own. Before Michael Collins made his spacewalk on Gemini 10, he trained extensively in these short bursts of zero-G. In early preparations for the moon landings, the flight paths were altered to simulate lunar gravity. Information gathered on these flights was used to modify spacesuit design to cope with the most difficult situations. Other scenarios worried NASA planners too. If an astronaut wearing his bulky spacesuit and heavy life support system fell over, would he be able to get back to his feet? The aircraft, flying a shallower parabola, was able to simulate lunar gravity for longer durations than for zero-G. Russia's Ilyushin IL-76 serves as the largest zero-gravity aircraft. Today, such planes are used for far more than training astronauts. They serve as microgravity laboratories, where equipment is tested and experiments are undertaken. Operators are even offering zero-gravity joyrides. The European Space Agency, in partnership with CNES, has 6 zero-G campaigns each year flying out of Mérignac Airport in the south of France. The A300 aircraft used for these flights is soon to be replaced by an A310. The rear of the aircraft, known as the free floating area, is padded and fitted with handrails. It is equipped with fixed benches for technical and biological experiments, which are the prime reason for the flights. Recently, the International Space Station began using a 3D printer. To make certain that it would function properly in microgravity, it was first tested aboard this zero-G flight. Human physiology, fluid mechanics, biology, combustion and basic physics are among the most studied disciplines.
Beautiful valley.
Really amazing.
By the end of the 1960s, NASA was prepared to send astronauts beyond Earth orbit, pushing hard to reach the Moon, but they were taking risks that today would be unthinkable. In October 1968, a Saturn V began inching its way to Cape Kennedy's Launch Complex 39, Pad A. There had been 2 previous Saturn V launches, but this one, Apollo 8, would be the first to carry a crew. Originally intended as a manned test of the lunar module in Earth orbit, flight objectives were radically readjusted when a lunar module could not be ready in time. The flight crew was changed too. Jim Lovell was the command module pilot, and though there was no lunar module, Bill Anders was the designated lunar module pilot. Frank Borman would command the revamped mission. The original Apollo 8 astronauts were moved to Apollo 9. They would be the first men to leave Earth orbit and fly around the Moon, and these astronauts had had very little time to retrain for this new mission.
15, 14, 13, 12, 11, 10, 9. We have ignition sequence start. The engines are on. 4, 3, 2, 1, 0. We have commit. We have liftoff. Liftoff at 7:51 a.m. Eastern Standard Time. We have cleared the tower.
On the previous Saturn V, harmonic vibration had caused the early shutdown of 2 engines. Action taken to rectify the problem saw a flawless launch for Apollo 8. 11.5 minutes after launch, the spacecraft, still attached to the upper stage, achieved orbit, with both the ground staff and space crew entering an intense period of system checking. This was a risky mission. A less public reason it had been brought forward came from the CIA. Intelligence suggested that Russia was preparing a lunar orbital mission.
Apollo 8, Houston. Go ahead, Houston. Apollo 8, you are go for TLI, over. Roger, understand, we're go for TLI.
TLI, translunar injection. Soon after, the S-4B upper stage fired, pushing Apollo 8 out of Earth orbit toward the Moon. Now, a new problem arose. Frank Borman began to feel sick and threw up, which was even more unpleasant in zero gravity. Because of the attitude of the spacecraft, they could not see the Moon, but through the round window they began seeing more and more of the Earth. Soon they would be the first people to see our planet in its entirety. However, this window soon fogged with gas from the oils in the chemical sealant. Apollo 7 had also suffered from this problem. As Apollo 8 approached the Moon, the crew prepared for an engine burn that would place the craft in lunar orbit. The main engine had to fire for 4 minutes when the command module was behind the Moon, out of radio contact. This was the first time that the crew got a decent view of the Moon. William Anders prepared to photograph the lunar surface. An important part of the mission was to document areas such as the Sea of Tranquility in preparation for future lunar landings. Then on the fourth orbit, they saw something astounding.
Oh my God, look at that picture over there. There's the Earth coming up. Wow, is that pretty?
After this mission, it was often said that they went to the Moon and discovered the Earth.
You got a color film, Jim? Hand me a roll of color, quick.
Oh man, that's great. Where is it?
Quick.
After 10 orbits of the Moon, Apollo 8 fired its main engine and began its return to Earth.
Just grab me a color. A color exterior. Hurry up.
During its cruise back, Bill Anders captured more pictures of the Earth. The Apollo 8 astronauts returned as heroes. Their flight around the Moon had put NASA's space effort back on the front pages. But it was the end of 1968, and there was only 1 year left to reach the Moon within President Kennedy's deadline. Just 2 months later, Russell Schweickart, Dave Scott, and Commander Jim McDivitt were preparing for the next Apollo mission. Apollo 9 would be the first test of the complete Apollo system. Till now, the lunar module had made only one flight when it was tested without a crew. This would be the first time 2 spacecraft had been launched together. And, like all Apollo missions, it would be far more complex than the mission that had preceded it. A February launch had been delayed to March 3rd, 1969, to allow the crew to recover from a virus they had contracted. Though Apollo 9 would remain in Earth orbit, the crew faced a punishing schedule. Not only would they be the first to fly the lunar module, but a spacewalk had been planned to test the new self-contained life support system. After reaching orbit, the command and service modules separated from the S-4B upper stage that carried the lunar module. They docked with the lunar lander to withdraw it from the S-4B. After separation, Apollo 9 backed away to a safe distance, and ground control sent the discarded stage on a course towards the Sun. The next few days were spent in manoeuvres, with the main engine being fired 5 times, changing the orbit in preparation for testing of the lunar module and to simulate mid-course corrections that would be needed on a trip to the Moon. The crew had removed the hatches and probes to clear the connecting tunnel between the command module and the lunar module that had been named Gumdrop and Spider. These were the first NASA craft to be named since Gemini 3's Molly Brown. Every aspect of the linked spacecraft was closely monitored in mission control. Soon, McDivitt and Schweickart would fly in a machine that had no capability of returning to the ground, and nothing could go wrong. In case something did go wrong and the two craft could not dock again, a spacewalk had been planned to test an outside transfer between Spider and Gumdrop. This was the Apollo program's first spacewalk, and Rusty Schweikart was only connected by a nylon tether. All his oxygen and electrical power came from the portable life support system he wore on his back.
Okay, Dave, come on out.
Both spacecraft had been depressurized, and while Schweikart was busy at the lunar module, Dave Scott was retrieving an experimental sample from the outside of the command module. This spacewalk was cut short because Schweikart was suffering from space sickness.
Okay, we're nice and stable with respect to you.
The next day, Spider and Gumdrop separated for the first time.
It's a nice looking machine. So is yours.
Using its descent engine, Spider, the lunar module, withdrew to a distance of around 150 kilometers. The next time Dave Scott in the command module saw the lunar module, it had jettisoned its lower descent stage. All engine tests for both stages had worked well, and NASA was developing confidence in their new moon craft. Before redocking with the command module, McDivitt and Schweikart did a complex series of pirouettes to allow Scott to inspect Spider from every angle. When the three astronauts were reunited, the lunar module was jettisoned, eventually to burn up in the Earth's atmosphere. They spent several more days in orbit photographing the Earth before splashing down in the Atlantic. NASA had just 9 more months to meet President Kennedy's end-of-the-decade deadline for putting a man on the moon, but there was one more step before they made the first attempt to land.
All stages pressurized.
Apollo 10 would take a lunar module to the moon and descend toward the lunar surface, but it would not land. In keeping with NASA's very tight schedule, it had a long list of questions to answer, and the mission would have the most experienced crew of any Apollo mission so far. Lunar module pilot Gene Cernan had flown on Gemini 9. Command module pilot John Young had flown on Gemini 3 and 10. And Commander Tom Stafford had flown on Gemini 6 and 9. One of the important problems that this mission had to solve was linked with the moon's uneven gravitation. Previous manned and unmanned lunar orbital missions had discovered that variable concentrations of mass within the moon had caused lunar orbits to be erratic. NASA needed to map these irregularities to fully understand how their spacecraft would perform in lunar orbit. 9.
We have ignition sequence start. Engines on. 5, 4, 3, 2. All engines running. Launch commit. Liftoff. We have liftoff 49 minutes past the hour.
Apollo 10 would be a complete rehearsal for the first lunar landing. It would be the second Apollo craft to leave Earth orbit. Docking with and extraction of the lunar module, which had been the major focus of previous missions, was becoming commonplace.
Okay, it's looking real stable to us. We show you closing finally. Roger. Snap, snap, and we're there. Got 2 grays. Roger.
Apollo 10 was the first spacecraft to make colour television transmissions, and they pulled in audiences of around 1 billion.
Do whatever he says.
As in the previous mission, Apollo 10 had 2 spacecraft each needing a different call sign. The astronauts had elected to call the mothership Charlie Brown and the lunar module Snoopy after the popular Peanuts cartoon strip of the time. After this, the space crews were asked to choose names that had a little more gravitas. When they disappeared behind the moon, they fired the main engine for 6 minutes, which the astronauts described as being interminable. The craft went into lunar orbit as planned, and 6 hours later, Stafford and Cernan entered Snoopy to prepare it for descent toward the lunar surface. It was teeming with weightless flakes of mylar insulation that had come loose when the connecting tunnel had pressurized. This caused itching for the rest of the flight. But there were more problems.
Charlie Brown, Houston, we're concerned about this yaw bias in the LEM and apparent slippage of the docking ring. We'd like you to disable...
The lunar module was more than 3 degrees out of alignment with the command module, and air pressure in the tunnel between the two craft could not be released. Houston was worried that undocking now could damage the latches that held them together. Engineers on the ground decided that anything less than 6 degrees was not a problem, and Snoopy was given the all clear to undock. This was the first time a lunar module had flown in the lunar environment for which it had been designed. Mission planners were concerned that Stafford and Cernan might try to seize the opportunity to make an unauthorized landing, so Snoopy had been short-fueled. If they did land, they could not get back. For the next 8 hours, John Young would be alone in Charlie Brown.
Houston, Charlie Brown, how do you read on high gate, over? Charlie Brown, Houston, over. Roger, read your line clear. Snoopy was go for DOI. Roger, great. Sounds great. We copy.
Snoopy dropped lower and lower, passing directly over the proposed landing site for the next Apollo mission and travelling more than 500 kilometres from the mothership. But just before they were due to jettison the descent stage, a guidance setting switch was in the wrong mode, and the lunar module began gyrating wildly. By dumping the descent stage and switching to manual control, Tom Stafford was able to regain stability.
Charlie, how was the stage? Good, huh? Wait till that thing blinks. Charlie Brown, Houston, they got staging. They had a wild gyration, though, but they got it under control, over.
The rendezvous went according to plan, and Apollo 10 remained in lunar orbit for another 29 hours, mapping anomalies in the lunar gravity before returning to the Earth. But even as they were near the moon, another Saturn V had been rolled out to the launch pad. Apollo 11 was being prepared for the first attempt at a landing on the moon.
Allumage Vulcain. Allumage des EAP.
ESA, the European Space Agency, launches light, medium and heavy lift rockets from its facility in French Guiana, but it has no ability to bring vehicles back through the Earth's atmosphere for a safe landing. The Intermediate Experimental Vehicle, or IXV, is being developed so that ESA can master the techniques of controlled re-entry from low Earth orbit. The IXV uses the lifting body concept in combination with ceramic and carbon fibre thermal protection. Though this is a more complex technique than the common ablative heat shield made of plastic resin that dissipates heat as it vaporizes, ESA wants to test a vehicle that offers greater control for more accuracy in landing. The concept vehicle will function autonomously. It is equipped with thrusters to maintain the correct attitude before it reaches the Earth's atmosphere. As it descends to 120 kilometres, the IXV encounters the upper levels of the atmosphere. At this point, it is travelling at a speed approaching 27,000 kilometres per hour. Two flat actuators keep the craft correctly aligned during this part of the re-entry. There are unanswered questions about this part of the journey where the oxygen and nitrogen molecules in the air become a high-temperature plasma that does not obey the usual rules of aerodynamics. At an altitude of 26 kilometres, the craft will have slowed to 1,600 kilometres per hour, where the first of a series of supersonic parachutes is deployed. Though this technology is well understood, ESA still had to perform drop tests in the Mediterranean of a dummy IXV to see how their craft would behave. In mid-2014, the craft was prepared for its flight from the European spaceport in Kourou. The IXV was covered in more than 300 sensors to monitor its behaviour during all phases of its 2-hour flight.
4, 3, 2, 1, top. Allumage P80, décollage.
It will be 6 months before the technical data has been fully understood and can be used in the design of a larger re-entry vehicle. For more than 15 years, Europe has been working on its own satellite navigation system. Called Galileo, the system is intended as a civilian global location service as an alternative to the American GPS, which has military applications. This means average GPS users can have their service downgraded without notice. An in-orbit validation phase, using 4 satellites, was recently completed, and new additions are being launched regularly until a constellation of 30 satellites is in service. Satellites 5 and 6, known as Dorisa and Milena, were sent up on August the 21st, 2014, aboard a Soyuz launcher. Initially, everything seemed to have gone well, but a design flaw in the frigate upper stage allowed fuel lines to freeze during the extended cruise, and the satellites were delivered to elliptical rather than circular orbits. It took a while just to find where Dorisa and Milena were, and then ground staff began the detailed calculations involved in bringing the satellites back to usable positions. The low end of the orbit took both satellites through the Van Allen radiation belts, endangering the sensitive navigational electronics. Using the satellite's own manoeuvring thrusters, they were brought into usable circular orbits. After exhaustive systems checks, Dorisa and Milena were given a clean bill of health and, though their positions are not ideal, they will still be able to contribute to the Galileo constellation's function. Soon the next 2 satellites, Adam and Anastasia, will go into orbit, although their launch has been delayed by a thorough review of the Soyuz and its frigate upper stage. It has been determined that the proximity of a cold helium line to the fuel line caused the freezing problem in the frigate. As the Apollo program was preparing to land on the moon, some saw it as the beginning of a glorious age of exploration, while others were seeing it as the end of an expensive drain on the American budget. Early on July the 16th, 1969, vast numbers were gathering along the beaches of central Florida to witness history. The American people had been preparing for this moment for almost a decade since the late President Kennedy had responded to the Soviet Union's early superiority in space technology by setting a trip to the moon as a national goal. More than 1 million people were crowding the roads and causeways around Cape Canaveral that had recently been renamed Cape Kennedy. Minor dignitaries and friends and families of space workers had access to special stands constructed in the grounds of the Kennedy Space Center to see the Apollo 11 astronauts blast off. While the public had great faith in NASA's ability to land men on the moon, the experts working in the space business put their chances of success at no better than 50-50. The astronauts had spent long hours in simulators preparing for every eventuality, yet the equipment they used for practice only provided an approximation of conditions in space, with some of the test rigs appearing bizarre. A special gantry built at NASA Langley provided something approaching the experience of lunar gravity. Hours before the scheduled launch, the giant Saturn V was slowly taking fuel. Its tanks would be constantly topped up till seconds before liftoff. Michael Collins was the command module pilot. He'd flown previously on Gemini 10. Buzz Aldrin was the lunar module pilot. He'd pioneered new techniques for spacewalking on Gemini 12. And the mission commander was Neil Armstrong. On Gemini 8, his cool head and quick thinking had saved the mission from tragedy. Apollo 11 would have a fully experienced team chosen to deal with and solve difficult problems. And there would be problems. Every NASA mission had built on the experience of previous missions, but there was always a point when they entered unknown territory, and the pressure to reach the moon before the end of 1969 had been unrelenting.
We're going to the moon together.
But American people were supremely confident, and launch parties were held across the country. Local entrepreneurs were quick to capitalise on the mood of celebration.
The swing arm now coming back as our countdown continues.
At the Kennedy Launch Center, tension was high. The German-born rocket pioneer, Wernher von Braun, his whole life had been leading up to this moment.
Below we have a team of technicians working.
Everyone at the Cape understood how many different components had to work correctly for a successful launch. Astronauts agreed that the launch made them most anxious.
Firing command coming in now.
This would be the 6th launch of the Saturn V booster, and while some of these flights had been a little lumpy, all were regarded as successful.
T-minus 15 seconds. Guidance is internal. 12, 11, 10, 9. Ignition sequence start. 6.
Just seconds into the flight, control was transferred from the firing room in the launch complex to mission control in Houston.
Apollo 11, this is Houston, radio check over.
12 minutes after launch, Apollo 11 was in low Earth orbit. Apart from a slightly rough ride with the third stage, everything had been routine.
5x2, very weak. Can you give us a status report, please?
Trans-lunar injection and docking with the lunar module were now practices that had been done many times before, and they too were achieved with little fuss.
Oh, well, it's clear out, Mike, and we understand that you are docked. That's fine.
The cruise to the moon and lunar orbit had been done twice before, and flight manuals and checklists had all been rewritten with the benefit of previous experience. The Apollo system had been designed so that all the navigation information and engine burns could be made autonomously by the crew, but radio ranging techniques had improved so rapidly that mission control was now giving all instructions. However, the crew still used the onboard technology to determine their position in case of a communications problem. Command module pilots took pride in the accuracy of their navigation. Both the command and lunar modules were equipped with the Apollo guidance computer, one of the first practical microcomputers.
We recommend you accept the nav 49, continue through your sequence of sightings, and then we'll...
For most computations, there was a manual workaround, but for the complex flight path required for the lunar module to land on the moon, the flight computer was essential.
Turn your angle 47, something be a little high. Stand by.
Now in lunar orbit, the crew of Apollo 11 would lose radio contact every time they passed behind the moon.
44 over. Yeah, roger.
During the 13th orbit, the lunar module separated from the command module.
How does it look? The Eagle has wings. Right.
The two craft now adopted individual call signs. The command module became Columbia, and the lunar module was now Eagle. Descent to the moon happened in 3 separate stages, each controlled by its own computer program.
Roger, let us know when you're ready to copy. We have a DOI pad.
The first stage was the braking phase that changed the orbit so it would reach a zone above the designated landing point. During this period, the crew were travelling feet first, looking up at the Earth. The next stage was the approach phase, when the Eagle tipped up into a more vertical attitude. This was when Aldrin and Armstrong got their first view of the landing point. A long elliptical region in the Sea of Tranquility was their target. The open plain was judged to be the easiest place for the first lunar landing.
Altitude lights out.
Now, unexpected things began happening. Fuel in the lunar lander's tanks began sloshing around. While this was not dangerous, the motion meant the craft could give no clear indication about its pre-programmed landing site.
Program alarm. 1202. 1202. Give us a reading on the 1202 program alarm.
Then the flight computer began sounding an alarm, and there was only one person in mission control that knew what a 1202 alarm was. A young software engineer understood the computer was overloaded, but that it could still look after critical functions.
Roger, Delta H is looking good to us.
The mission would continue.
Roger, we got you. We're going at alarm.
The final part of the landing sequence was still computer controlled, but it allowed the commander to override the craft's rate of descent and its positioning. As it was heading for a field of large boulders, Armstrong took control, looking for an appropriate landing area.
100 feet, 3.5 down, 9 forward.
This took a lot longer than anyone expected.
185. 75 feet. Car's looking good, down a half. 6 forward.
Fuel was running low.
60 seconds. Lights on. 6. Down 2.5. Forward. Forward. That's 40 feet down 2.5. Picking up some dust. 30 feet, 2.5 down. Straight shadow. 4 forward. 4 forward. Drift into the right a little. 20. Down a half. 30 seconds. Forward. Just. Good. Okay. Contact light. Okay, engine stop. ACA at a detent. Mode control both auto. Descent engine command override off. Engine arm off. 413 is in.
The relief in mission control was palpable.
We copy you down, Eagle.
Listen, Tranquility Base here. The Eagle has landed.
Roger, Tranquility. We copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot.
Thank you.
Because of the distractions during the descent, no one had a clear idea of the Eagle's exact location.
Master arm on. Take care of the descent.
After the craft was made secure, the flight plan called for the astronauts to get some sleep. But Armstrong and Aldrin requested a change, which was agreed to. They began preparing for their walk on the lunar surface. Around 7 hours later, Armstrong was climbing down the ladder.
Depressed in the surface about 1 or 2 inches.
A black and white TV camera was now activated, and around the world, 600 million people were watching.
That's one small step for man, one giant leap for mankind.
This was something new. No one had thought that history would be televised with the world as witness. It had even been argued that television was a waste of time. Now NASA was rescheduling future missions so their astronauts would step onto the moon in prime time. Armstrong and Aldrin spent 2.5 hours on the lunar surface, and much of that time was used in ceremonial duties such as planting the US flag and chatting to the president. The trip back to lunar orbit went smoothly. From here, the 3 astronauts were back on thoroughly understood ground. The 3-day return cruise to Earth was a calm period before a storm of publicity obligations that the Apollo 11 astronauts had not prepared for. Armstrong, Aldrin and Collins were feted in ticker-tape parades across the United States and then across the world. The generous taxpayer funding that had kept the space program going was now in doubt, and NASA was keen to build on this wave of popularity. But in the corridors of power, questions were being asked about the vast sums required to put men on the moon. With the last landing of the shuttle fleet in 2011, the United States, a major contributor to the International Space Station, was reliant upon Russia to ferry astronauts to and from the orbiting laboratory.
3, 2, 1, 0.
But to get cargo and supplies to the ISS, NASA signed contracts with private space technology company SpaceX. SpaceX's cargo capsule, known as Dragon, has regularly been delivering hardware and consumables to orbit since 2012. Dragon can also return from orbit. It's a stepping stone to the company's Dragon version 2 crew capsule that will be able to take astronauts to and from space. Due to make its first manned flight in 2 years, the Dragon takes advantage of new materials and technologies to cut the cost of spaceflight. Its return through the atmosphere will make use of an ablative heat shield, and the current generation of Dragons return via conventional parachute technology. But the new capsule will use propulsive deceleration technology to make a pinpoint landing, enabling it to be reused. The Falcon 9 launcher's 2 stages will also return to the ground for reuse. A Grasshopper technology demonstrator made its first flight in 2012. SpaceX conducted a series of experimental launch and return flights at its test site in McGregor, Texas. The vehicle made 8 successful flights to refine the autonomous return technique. The technology has been incorporated in the Falcon 9. After launching a cargo craft, the booster's first stage attempts to return to an ocean platform. SpaceX technicians are aware that further refinements are needed. In 2006, the European Space Agency began work on a unique star mapper that became known as Gaia. Designed to orbit the Sun at a point 1.5 million kilometres beyond Earth, it will rotate, scanning our local galaxy to accurately gather positional information about the neighbouring stars. 2 different telescopes feed images to the probe's very large high-definition camera. Over its 5-year operational period, Gaia will rescan the same areas 70 times. As it orbits the Sun, its positional change will enable it to observe parallax differences from which accurate star distances can be determined. In addition to position and distance information, Gaia will collect 2 different types of spectral data. One will help determine the stellar object's speed, and the other will indicate the object's chemical makeup. Gaia was successfully launched at the end of 2013 and has been functioning correctly since. Its pointing and positioning are achieved by cold nitrogen thrusters that do not compromise the satellite's thermal integrity. Gaia's data link with Earth can handle 3 megabits per second, and it will be fed back to ESA's most sensitive ground stations at Sobreros, Spain, and New Norcia in Western Australia. The largely ceremonial first moon landing was over, and as NASA was preparing for the scientific missions, politicians were preparing big cuts to the space program. Toward the end of the 1960s, America finally had something to celebrate. Armstrong, Aldrin and Collins had returned safely from the moon. For America, the decade had started with an uncomfortable realization. Cold War adversary, the Soviet Union, had a commanding lead in space technology. The United States had been seized by a wave of anti-communist paranoia. Nine years and $17 billion later, Apollo 11 had planted the US flag on the surface of the moon.
First set foot upon the moon, July 1969, AD. It came in peace for all mankind.
Around the planet, 600 million people had watched on TV. The world's population was watching history, and they knew it.
Tranquility Base, this is Houston. Can we get both of you on the camera for a minute, please?
At beaches and rivers in central Florida, 1 million Americans had turned out to see the launch of Apollo 11. November the 14th, 1969, was a wet day at the Kennedy Launch Center. Numbers that turned out to watch the launch of Apollo 12 had dropped by 2/3. After the huge viewing numbers attracted by Apollo 11, NASA upgraded all aspects of the television coverage for the remaining moon landings. Pete Conrad would command the mission with rookie Alan Bean and command module pilot Dick Gordon. Their destination, the Ocean of Storms, just near the landing site of Surveyor 3, the unmanned craft that had touched down 2 years earlier.
6, 5, 4, 3, 2, 1, 0. All engines running. Commit. Liftoff. We have liftoff. 11:22 a.m. Eastern Standard Time.
The driving rain was not seen as a problem. Although high winds could delay a launch, the Saturn V was an all-weather vehicle, and the wet conditions were not a factor.
Roger, clear the tower. I got a pitch and a roll program, and this baby is really going. Roger, Pete.
Soon after liftoff, lightning struck Apollo 12 and ran down the ionized exhaust trail to the launch tower.
We had everything in the world drop out. Roger.
All instrumentation in the command module went haywire, and telemetry readouts on the ground were showing garbage.
Apollo 12 Houston, try SCE to auxiliary, over.
For a short while, nobody in the craft or on the ground knew what had gone wrong.
SCE to auxiliary.
Finally, the crew was asked to flip an obscure reset switch. Only Alan Bean knew where it was. It restored all instrumentation, and the mission could continue.
Apollo 12 Houston, go for staging. Some really big pitch, gang. Got a good S2, gang. Roger, we copy, Pete. You're looking good.
This had happened at a critical period of powered flight, and Mission Control had come very close to calling an abort.
Your thrust is looking good, Pete.
The single Earth orbit was spent checking all systems before Apollo 12 was given the all-clear to go to the moon.
Right, Pete, your fuel cells look good down here.
After the huge television audiences for the Apollo 11 lunar mission, NASA had equipped Apollo 12 with a colour camera so that audiences around the world could see higher quality pictures from the surface of the moon. The second landing on the moon benefited greatly from design changes derived from the Apollo 11 experience. Baffles inside the lunar module's fuel tanks prevented unwanted sloshing that had confused the flight computer.
Yeah. 81, 32, 36. Coming down.
The landing went exactly as planned, with the astronauts recognizing all the landmarks in the vicinity of the Surveyor 3 probe.
He's got it made. Come on in there. 24 feet. Contact light. Roger, copy contact. TV starting to...
But as Pete Conrad climbed toward the lunar surface, in the United States, it was 6 a.m. on a Tuesday morning, and very few people were watching the live television pictures.
I bet you when I get down to the bottom of the ladder, I can see the surveyor.
Viewer ratings were important for NASA. They knew keeping the American taxpayer on side was an important part of convincing politicians that the space agency's generous funding should be maintained.
I'm going to step off the pad, Mark.
As Alan Bean joined Conrad on the lunar surface, he grabbed the TV camera to relocate it and inadvertently pointed it at the sun.
Yeah, pull the hatch closed here. Okay. Don't lock it.
They were the last live Apollo 12 TV pictures from the moon. The pinpoint landing, the much longer stay on the moon, and the larger volume of return samples all made Apollo 12 a technical success. But NASA had wanted to keep the American public engaged with the space program, and the only pictures anyone saw were short film grabs. Americans were losing interest in space. After the return of Apollo 12, there were still 8 more Saturn V launch vehicles in production, enough to stretch as far as Apollo 20. But in January 1970, Apollo 20 was cancelled, and soon the planned Apollo 18 and 19 missions were also scrapped. As NASA was preparing to reap the benefits of space engineering and lunar research, the program was being curtailed. Things would change slightly for Apollo 13. NASA rescheduled the mission's lunar activity to coincide with prime viewing time across the United States. This would cost TV networks money, and they were not happy. Commander Jim Lovell had flown around the moon as command module pilot on Apollo 8. This would be his 4th spaceflight. His colleagues were both first-time astronauts. The lunar module pilot was Fred Hayes, but the third member of the team had come from the backup crew just 3 days before launch. Command module pilot Jack Swigert replaced the original crew member Ken Mattingly, who had been exposed to German measles. Mattingly watched the launch from Mission Control in Houston.
9, 8, ignition sequence has started. 6, 5, 4, 3, 2, 1, 0. We have commit and we have liftoff at 2:13.
Its objective on the moon was the Fra Mauro Highlands, named after the adjacent Fra Mauro crater.
And it has cleared the tower.
My booster then bored out was way early.
During powered flight, a second stage engine cut out early. The remaining units burned for slightly longer to compensate, but this was no major problem.
Not right now, flight. All the other engines are go.
Okay, Joe, I'm pointing over toward Jack, and it's pretty...
Translunar injection happened smoothly, and the crew soon pulled out their colour TV camera to entertain the people back on Earth. But apart from the people in Mission Control, no one was watching. The TV networks failed to broadcast the transmissions sent from Apollo 13.
Dane, we've got one more item for you when you get a chance. We'd like it to stir up your cryo tanks.
Soon after they had ceased their transmission, with the spacecraft 3/4 of the way to the moon, an explosion took out the command module's main power supply.
Say again, please.
Houston, we've had a problem.
Nobody understood what had happened, but it soon became obvious that Apollo 13 would not land on the moon.
Stand by 13, we're looking at it. Jack, Aquarius,
With the command module effectively dead, the lunar lander now became the astronaut's sole source of power. Its descent engine would be used for all course corrections. The spacecraft continued out and around the moon on a free return trajectory.
No, that's an Atlantic landing site.
A landing in the South Atlantic would get them back quickest, but there were no recovery ships in that area. Before Apollo 13 disappeared behind the moon, ground staff began recalculating the burn that would return the craft to the Pacific Ocean. While there was enough food and oxygen to last till the return to Earth, water and power would be critical. Before long, temperatures in the craft had dropped to near freezing. With strictly rationed water, Fred Hayes got a urinary tract infection. The plan was to restore power to the command module using the re-entry batteries just before they hit the Earth's atmosphere. This had never been done before, so a team of experts, including Ken Mattingly, began experimenting with different procedures in a simulator. NASA's space program was back in the headlines, but not for the reasons they wanted. Simulations of the power-up sequence were complicated because condensation, caused by the low temperatures in the command module, threatened to short out the electrical system. But finally a procedure was radioed to the crew. The rescue showed NASA at its best, creatively solving difficult problems as they arose and returning the 3 astronauts safely. Apollo 13 would become known as a successful failure.
Roger, sufficient. Thank you. Cameras and
Alan Shepard was NASA's first man in space. Though his Mercury capsule, Freedom 7, had only flown for 15 minutes, he was destined to become an important part of America's space program. In 1964, he was diagnosed with Meniere's disease and suspended from all flight activities. He spent the Gemini program as chief of the astronaut office. After corrective surgery, he was restored to flight duty and eventually was made commander of Apollo 14. His command module pilot was Stuart Roosa, and the lunar module pilot was Ed Mitchell. Apollo 14's objective was Fra Mauro, the same area in the lunar highlands that had been targeted by the aborted Apollo 13. It would be the last of the H-type missions that carried no vehicle.
5, 4, 3, 2, 1, 0. Launch commit. Liftoff. We have liftoff with Apollo 14. 3 minutes past the hour.
Finally, after almost 10 years, Alan Shepard was back in space. Not long after Apollo 14 reached orbit, his space flight time had doubled. Like all previous Apollo missions, it would be more complex than the one that preceded it. And like all Apollo missions, there would be problems. Docking with the lunar module should have been routine, but on this occasion, the mechanism would not lock. After 5 attempts, there was still no success.
Okay, Houston, we've hit it twice.
On the 6th attempt, Stu Roosa made a more aggressive use of his thrusters, and the 2 craft locked together.
We got some, Houston. I believe I got a hard dock, Houston. Okay, we seem real steady. I'm going to...
In lunar orbit, after the lunar module Antares had separated from the mothership Kitty Hawk, the landing computer began flashing an alarm. The abort switch had an intermittent short that would trigger an automatic abort sequence if it happened during the powered stage of Antares' descent to the surface. At Mission Control, though they couldn't fix the switch, they decided to reprogram the computer so it would ignore the spurious alert. They had 2 hours to work out the new code. It fell to MIT programmer Don Iles, who came up with a workaround. The new sequence was tested in a simulator, and then the 61 keystrokes required were read up to the astronauts. The landing proceeded with pinpoint accuracy.
30 feet per second, looking straight. 20 feet, 10, 3 feet per second, contact now. 2, stop. 3, whoa. Okay, we made a good landing.
The lunar module had landed on a 7-degree incline that made moving in the cabin difficult. They were about 1 kilometre from the rim of Cone Crater, where they were scheduled to collect samples during their second moonwalk. As with every successful Apollo moon landing mission, the astronauts unfurled the American flag. Before Apollo 11, it had been proposed that the United Nations flag be planted, but Congress had passed a law stating that no flag other than the stars and stripes could be deployed. During previous lunar missions, astronauts had spoken about how difficult it was to judge distances and to recognise landmarks. Shepard and Mitchell were tiring during their climb toward the rim of Cone Crater. Doctors at Mission Control monitoring their heart rates became concerned. They were ordered to return without realising they were only 20 metres from their objective. But NASA was about to eliminate this problem. Apollo astronauts were training with a new piece of hardware. All remaining missions would be able to travel 10 times further from the lunar module using the new lunar rover. Geology was the main feature of the remaining Apollo missions. Preliminary analysis was showing that the moon had once been molten with rocks containing no trace of water. Dave Scott would command Apollo 15. Jim Irwin was the lunar module pilot. This would be his first spaceflight. Al Warden was the command module pilot. Apollo 15 was also his first spaceflight. Refinements in the design of the Saturn V launch vehicle and improvements in the targeting and trajectory parameters meant that a heavier version of the lunar module could now reach the moon, carrying heavier loads.
Liftoff. We have liftoff at 9:34 a.m. Eastern Daylight Time.
The new expanded missions were called J missions. Not only could they take more to the moon, they could bring a greater mass of lunar rock back to the Earth. Their target on the lunar surface was Hadley Rill, a peculiar winding groove, probably formed by ancient volcanic activity. The landing site was in the lunar northern hemisphere near the Apennine Mountains. Separation of the lunar module Falcon from the command module was delayed by a hatch problem, but this was soon solved. Landing techniques were now so refined that Scott was easily able to compensate for an early 6-kilometre aberration and set Falcon down for another pinpoint landing.
Okay, Houston, the Falcon is on the plane at Hadley.
The quality of television pictures from the moon had continued to improve as audiences across the United States dwindled. The big difference was the rover. Not only would it allow the astronauts to travel further and to carry more samples, but without exerting themselves, Scott and Irwin used less oxygen and could stay longer on the surface. Dave Scott had taken his geology training very seriously, and on the crew's second traverse in the lunar rover, this training paid off.
Okay, that's as good a way as any.
They discovered a white rock at the bottom of the Hadley Rill, which was thought to be part of the lunar bedrock. It became known as the Genesis Rock, and it was more than 4 billion years old. After almost 3 days on the moon, Scott and Irwin prepared the Falcon for return to lunar orbit.
Good liftoff, automatic.
There had only been a few minor glitches during the earlier parts of the mission, and rendezvous, docking and the cruise back to Earth continued to remain problem-free. During the final descent, the remaining highly corrosive fuel from the capsule's thrusters was dumped, but this time it caused the collapse of one of the craft's 3 parachutes. Further damage would have been catastrophic. As 1972 commenced, there were only 2 remaining Apollo missions. Though the lunar expeditions were increasing in duration and complexity, the American people had lost interest, and so had the political administration. Life-threatening difficulties occurred on every flight, but NASA had been so good at overcoming problems that the drama of lunar exploration was easily pushed off the front pages by war and political scandal. When the last ever mission to the moon blasted off at night during prime time, TV networks were annoyed that launch delays messed up their viewing schedule. Astronaut Gene Cernan would be the last man to walk on the moon, and with the return of Apollo 17 to the Earth, lunar exploration stopped. There are no plans to return to the moon. The Space Shuttle was designed as a cost-effective way of making travel to low Earth orbit routine, but the promise of cheap and easy access to space had unexpected consequences. During the 1960s, while NASA was striving to reach the moon, a feasibility study was carried out into a space plane that could be reused. Politicians were wincing at the costs involved in giant boosters that could only be used once. A craft that could take off like a rocket and return to the ground landing like a plane was touted as an economical alternative to disposable rockets. Concepts for a space plane had been around since the 1950s, but most of these had been little more than drawings backed up by a modest set of calculations. In the early months of 1972, a formal agreement was signed and NASA began work on a reusable space launch system that became known as the Space Shuttle. A fleet of 4 shuttles was planned, and they would all be named after famous ships. However, an extra shuttle to be used as a test craft was completed first. It was to be named the Constitution, after the famous US naval frigate. But fans of the TV show Star Trek petitioned the government to call it the Enterprise after the fictitious spaceship. As it rolled out from the plant in Palmdale, California, Star Trek fans were there in force. Fortunately, there had been several real ships named the Enterprise, so the administration relented and the new name stuck. Compared to the space capsules in which astronauts had previously returned to Earth, the new machine was huge and testing presented huge problems. NASA modified 2 747s to carry the Enterprise to varying altitudes for a series of approach and landing tests. With no engines, it had to glide to a landing, but gliders are light with long wings, and the shuttle was heavy with only stubby wings. It would hit the runway at incredibly high speed. The Enterprise made 5 non-captive flights, spending a total of just 19 minutes in the air. When Columbia, the first space-worthy shuttle, left the factory, big claims were being made for the new system. It would drastically reduce launch costs, and there would be a new mission every week. But there were critics that felt this was far too optimistic. Veteran astronaut John Young would be commander on the first shuttle mission. His pilot was rookie astronaut Bob Crippen. This was the first time a completely new launch system had been tested with a crew on board. Young was instrumental in convincing NASA that Columbia's first flight should not be a test of the very risky abort maneuver that required the shuttle to flip and to return to the Kennedy landing strip. Columbia blasted off on its maiden voyage in April 1981. It had been almost 6 years since an American had flown in space.
Columbia, Houston, you guys did so good, we're going to let you stay up there for a couple of days. You're go for on orbit.
Columbia's first flight and the subsequent 3 missions were all designed to test the orbiter in space. Modifications would be carried out based on what was learned during these flights. The crew reported that insulating tiles on an engine pod had dislodged. The craft was covered in thermal tiles to protect it during the heat of re-entry. Problems with tiles would be an ongoing issue. Columbia returned to a safe landing and, though this first shuttle mission was a success, the orbiter had extensive tile damage and one of the undercarriage doors had buckled. Shock waves at launch were responsible for some of the damage, and the pad would be modified. But clearly the tiles were a vulnerable part of the design, and preparing the orbiter for reuse would take longer than expected. A new method for attaching the tiles was introduced, and engineers were confident other difficulties could be overcome. It took 103 days for NASA to prepare the spacecraft for its second flight. This would be the last flight with the large external fuel tank painted white, saving 272 kilograms. This time the commander was Joe Engel, with Dick Trugley as his pilot. The 4 shuttle test flights all had 2-man crews. Vital components in the new space transportation system were the 2 solid rocket boosters. The shuttle program marked the first use of solid-fueled rockets for human spaceflight. Unlike the liquid-fueled main engines, these boosters could be stored with a full propellant load. But once they were alight, they could not be controlled. They burned until their fuel was exhausted. They were then jettisoned. And, just like the shuttle, these boosters were designed for reuse. Waiting off the coast of Florida, recovery ships tracked their path back to the ocean. They fell from a height of 67 kilometres with parachutes deploying at 4 kilometres. The recovery team collected the parachutes, pumped out the water and towed them back to NASA for refurbishment. After Columbia's second flight, NASA discovered an O-ring designed to seal the booster's individual sections was partially burned through. Extensive testing of the solid fuel booster with intentionally damaged O-rings did not lead to failure, and NASA concluded that the safety factor for this component was large enough. The remaining 2 launches in the shuttle test program saw the Space Transportation System take on a familiar look, with a large external tank remaining unpainted. Although the system was continually improved, this was the last change to its appearance. These test flights verified the shuttle's ability to cope with on-orbit thermal stress and allowed the crew to gain experience with the robot arm. But there was also a secret military aspect to one of these missions that sat awkwardly with the civilian space agency. Modifications to NASA's original design had been made to accommodate military payloads. After Columbia's successful return from its 4th mission on July 4, 1982, the spacecraft was declared operational. This meant it could start earning its keep, and NASA had big plans for its new launch system. But some were arguing that things were happening too fast. New aircraft had to accumulate thousands of safe flights before earning operational status. Over the next 3 years, Challenger, Discovery and Atlantis entered service, with the new shuttle fleet's primary objective being the deployment of commercial satellites. However, launches were nowhere near approaching the 1 per week figure claimed during the shuttle's design phase. An orbiter could carry 3 standard-sized communications satellites. The shuttle fleet began a series of commercial satellite deployments. And when faulty boosters left some expensive satellites in low Earth orbit, new satellite rescue missions were scheduled, and a completely new capability became available. The SolarMax satellite, launched in 1980, had lost its attitude control. This left it unable to continue its study of solar flares. But astronauts had been training for a unique repair mission. Nothing like it had been attempted, but NASA was keen to develop the new techniques that the shuttle system was making possible. A completely new device that allowed astronauts to fly freely had been built. NASA had plans for a space station that would require complex construction techniques, and the Manned Maneuvering Unit was seen as an important new tool for astronauts to master. The repair of SolarMax was its first proper task. However, capture of SolarMax did not go smoothly, with mission specialist George Nelson inadvertently imparting unwanted tumbling to the satellite. The spin was stabilised by ground controllers, and the next day, using the robot arm, SolarMax was grabbed and brought into the payload bay. Several instruments had failed, and it took 2 mission specialists 2 separate spacewalks to complete the intricate repair. The team was discovering that an astronaut mounted on the end of the robotic arm could move with great precision. Though the astronauts who flew it said the MMU responded well to manual control, more practice was needed before it could equal the accuracy of the robotic arm. The repair mission had been so successful that new Earth-orbiting satellites would now be redesigned for ease of maintenance. Though the new space transportation system was taking a long time to refurbish between flights, NASA was scheduling future missions at a greater frequency. The space agency was pioneering new procedures, and the shuttle's future looked bright. In 1984, there were 5 shuttle missions. In 1985, with Atlantis completing the shuttle fleet, this increased to 9 flights. The overwhelming majority of shuttle flights at this time involved the deployment of satellites, but there were some missions, like the Space Lab, that were dedicated to science, specifically the study of weightlessness on the human body. This saw NASA entering into a partnership with the European Space Agency. Space Lab was carried within the shuttle's payload bay, but NASA was aware that the Soviet space program was planning the launch of an orbiting space station. The construction of a space station had been a prime design consideration with the shuttle, and NASA had begun planning its own space station, but money for this project was not materializing. In January 1986, a crew of 7 was preparing for the launch of Challenger. Although Cape Canaveral in Florida has a generally warm climate, conditions leading up to the launch had been frigid. Launch facilities had frozen during the night, but NASA was keen to proceed, and though some voices were urging caution, they were overruled. The crew was to deploy a data and relay tracking satellite. But one of the mission's specialists was schoolteacher Krista McAuliffe.
We have main engine start, 4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
NASA saw this as an opportunity to rekindle enthusiasm for the space program and to illustrate how safe and routine spaceflight had become.
Program confirmed. Challenger now heading downrange.
Krista McAuliffe's parents were at the Kennedy Space Center to watch the launch. As Challenger climbed toward orbit, a rubber O-ring designed to provide a seal between the lower segments of the solid fuel booster began leaking flame.
Engines throttling up, 3 engines now at 104%.
Challenger, go at throttle up.
Challenger, go at throttle up.
73 seconds after launch, the inevitable happened.
Downrange distance 7 nautical miles.
The solid fuel boosters flew on aimlessly, and the disaster continued to unfold live on television.
Obviously a major malfunction.
A comprehensive inquiry determined that the extreme cold had caused an O-ring to fail. It led to a redesign of the boosters. The inquiry also determined that NASA management had a tendency to exaggerate reliability to the point of fantasy. Before the next shuttle could fly, every aspect of the space transportation system was scrutinized. New safety procedures were instituted as well. It was 33 months before Discovery was rolled to the launch pad in September 1988. From this point, the shuttle's range of duties had changed. The crew had a new safety regimen, and their flight suits had been modified. And significantly, there would be no more commercial satellite deployments. On the return to space mission, Discovery's major task was the launch of NASA's own tracking and data relay satellite, a replacement for the one lost in the Challenger disaster. Work on a replacement shuttle, Endeavour, was started. But even with a shuttle fleet back to full strength, the frequency of missions would never be as great as before the Challenger disaster. When shuttle flights resumed in 1988, its newly restricted duties blew a hole in NASA's business plan. The space agency still had ambitious scientific objectives, but fees from commercial satellite deployments would no longer flow. Major projects like the orbiting Space Telescope and what was now known as Space Station Freedom would have to be funded by the government.
1 minute, 30 seconds into the flight, all 3 auxiliary power units that provide hydraulic power to the orbiter.
While the shuttle was grounded, the Soviet Union had started assembling Mir, a space station that would serve as an orbiting laboratory. To NASA, this was good news. Cold War antipathy that had driven the race to the moon still existed, and Congress, not wanting communists to be ahead in anything, began allocating funds for design concepts for Space Station Freedom. Computer-generated vision of Space Station Freedom was produced, but not much else. The unthinkable happened. The Soviet Union collapsed, and, with the Cold War at an end, US politicians stopped funding Space Station Freedom. In 1989, Atlantis deployed the Magellan probe, which left Earth and successfully went into orbit around Venus. It was the first interplanetary probe to be launched from a space shuttle. Because Venus is shrouded in heavy cloud, its surface remained a mystery. Magellan used radar to map the planet, revealing unique surface features. Magellan had marked NASA's return to big science, and the shuttle had been an important part in the process. But a new project that would be impossible without the space shuttle was in train, and astronomers were very excited. Work on an optical telescope that would orbit above the distorting effect of the Earth's atmosphere had started in 1979, but delays in its construction had led to delays in its launch date. It became known as the Hubble Space Telescope, and just one of its unique design features was the hinged protecting panels that had door handles. It was designed to be maintained in space, and only a space shuttle could do that. April 1990, and the astronomy world held its breath.
Liftoff confirmed.
Finally, the most ambitious, most expensive telescope ever built was on its way to space, and the scientific breakthroughs from such a clear view of the cosmos were expected to be huge.
See the roll.
Discovery had a crew of 5, including pilot Charles Bolden, who went on to become the administrator of NASA. Discovery climbed to its highest orbit to date, 612 kilometres. The higher orbit would ensure Hubble's longevity. Apart from a small problem with its solar panels, the deployment of the telescope went smoothly. NASA and its European partners were hoping it would remain in service for at least 15 years. The first pictures from Hubble were blurred, and ground staff started adjustments to fine-tune the instrument. But in weeks it was apparent that there was a flaw in the primary mirror. Hubble became a laughingstock, the most expensive piece of space junk ever. Soon, plans for an elaborate mission to fix Hubble were underway, and the space shuttle was an essential part of a mission designed to turn a disaster into a triumph. But nobody was really sure if it would work, or even if it was possible. By the early 1990s, the space shuttle was changing the nature of missions to low Earth orbit, but an important part of its new role seemed to be fixing mistakes in sloppy satellite construction. Around the time that the orbiter Discovery had returned from its mission to deploy the Hubble Space Telescope, it was becoming apparent that while the mission had been a success, the telescope was a failure. A manufacturing error had been made and its images were blurred. Almost immediately, astronomers and engineers began formulating a repair mission. In principle, an optical correction could be made and fitted to the telescope, but nobody was sure if this was a practical idea. At this time, work on a new shuttle to replace the lost Challenger was nearing completion. Its first mission would also be a repair operation. In 1990, the communications satellite Intelsat 6 had been left stranded in low Earth orbit. Endeavour's crew would capture the satellite and attach a new booster to lift it to a geosynchronous orbit. They had been practicing in NASA's weightless training facility for 12 months before the mission. New equipment had been built for the specialist operation. Endeavour's first flight started in May 1992. The orbiter quickly caught up with the wayward Intelsat, and the mission specialists began the operation they had spent so long rehearsing. The plan called for astronaut Pierre Thuot standing at the end of the robot arm to snag the $180 million satellite with a capture bar. But the slow rotation of the satellite made the task impossible, and as Thuot continued to grapple with it, he induced more complex motion along all three axes of the 4-ton satellite. The attempt was abandoned and the orbiter backed off to a safe distance. After controllers on the ground had brought some degree of stability to the satellite, 3 astronauts entered the airlock, and Commander Dan Brandenstein brought Endeavour close in to the Intelsat and skillfully mimicked its remaining rotation. Then, in a spacewalk lasting more than 8 hours, the astronauts managed to grab the satellite with their gloved hands. This exercise had not been rehearsed and had been planned just hours before. The versatility of the shuttle and the ability it afforded its crew to rapidly adapt to real conditions saved the expensive satellite and added to the Space Transportation System's reputation for complex on-orbit tasks. After attaching a new booster and relaunching it, Intelsat performed for more than 20 years. But this first mission for Endeavour was still not over. A construction exercise designed to learn about building techniques in weightlessness was scheduled. NASA was keen to advance its space station concept. The main lesson from this exercise was that astronauts working with their feet securely anchored could carry out tasks in roughly the same time as they could in the ground-based simulator. But without a fixed anchor point, free-floating astronauts used most of the time in bodily orientation and work times increased. This had been one of the Space Shuttle's most productive missions so far. If crews working from the shuttle could capture and relaunch Intelsat 6, then it might just be possible to repair the dysfunctional Hubble Space Telescope. Soon, technicians at the Goddard Space Flight Center began working on an optical fix for Hubble. They also designed a suite of specialist tools needed for repair of the Space Telescope. Engineers had to earn dive qualifications so they could work with mission specialists in the giant pool at the Johnson Space Center. Here, the repair procedures were devised, tested, and then rehearsed. The 4 astronauts selected for the repair mission spent 11 months training in the underwater facility in Houston. In the pre-dawn hours of December the 2nd, 1993, Endeavour lifted off. It took the orbiter several days to catch up to Hubble, and the first thing the crew noticed was the buckle in one of the solar panels. Both panels were due for replacement, as they had induced unwanted vibration. Over the South Pacific, pilot Dick Covey manoeuvred Endeavour to within 9 metres of the telescope. Swiss astronaut Claude Nicollier from the European Space Agency captured the telescope with the robot arm and eased it into the payload bay. There were 5 spacewalks scheduled to undertake the array of tasks needed to bring Hubble up to operational specifications. Story Musgrave and Jeff Hoffman began by replacing the 2 gyroscopic remote sensing units that enabled the telescope to point accurately. There were problems closing the compartment doors, but by working together, the astronauts managed to get them back in place. The next day, Catherine Thornton and Tom Akers prepared to replace the solar arrays. One would be brought back to Earth for examination, but the damaged panel was discarded above Eastern Africa. The shuttle gently moved away to prevent any collisions. When the new units were connected, the corrective optics package was installed. During the next 3 days, a range of different tasks were carried out, not only to bring the telescope up to its intended specifications, but to give it new capabilities. After each modification, the Space Telescope Operations Center was able to verify the changes. NASA had completed one of the most challenging and complex missions ever attempted. The Hubble Space Telescope began delivering some of the most detailed visible light images ever seen. Its observations revolutionized our understanding of the universe. In the late 1980s, NASA had a problem. Confidence in the shuttle system had been shaken by the Challenger disaster. The Space Transportation System had been built as a stepping stone to something bigger, but NASA's plans for a space station had been starved of funds, and the shuttle's reason for existence remained unrealised. But in 1993, post-Soviet Russia and the United States signed an agreement on space cooperation. There had been a link-up between Apollo and Soyuz capsules in 1975, with the 2 craft coming together for 44 hours. But this had been largely symbolic. Now, post-Cold War Russia and the United States realised that they each had something that the other needed. Russia had Mir, a space station commenced in the Soviet era, but the country was strapped for funds. The US knew the Russians had expertise in orbiting outposts, and they wanted to learn from their experience. America had money, but not enough for their own space station. The Shuttle Mir program would serve as a bridge to something larger. In February 1995, Discovery rendezvoused but did not dock with Mir. It was the first shuttle to carry a female pilot, Eileen Collins. Over a 4-year period, space shuttles made 11 flights to Mir, and American astronauts spent 7 residencies on board the Russian space station. Shuttles also conducted crew exchanges and delivered supplies and equipment. American astronauts began riding to orbit on Soyuz spacecraft, something that continues to this day. US astronaut Shannon Lucid spent 179 days on Mir, giving her the American record for longest duration single space flight. In the Shuttle Mir program, Russia and America learned about long-term space flight and the building of orbital structures. They also learned about cooperation. But mistakes were made. In 1997, during Expedition 27, fire broke out when an oxygen generator overheated, and later, during the same expedition, a supply ship crashed into the space station while attempting to dock. Damage was considerable. Parts of Mir were now 11 years old, and with the knowledge gained during its operation, designers were certain they could build something better, particularly if they could take advantage of the shuttle's unique abilities. Plans for Space Station Freedom had morphed into a multinational collaboration on a replacement for Mir that would be known as the International Space Station. A memorandum of understanding between NASA and Rosavia-Cosmos saw the International Space Station as a laboratory, observatory and factory in low Earth orbit. In November 1998, a Proton rocket carrying the first piece of the International Space Station blasted off from the Baikonur Cosmodrome. Known as Zarya, it was soon visited by the shuttle Endeavour that attached a second piece called the Unity node. It was the first assembly mission. During the subsequent construction phase, most of the Russian components would dock automatically, while the American and European pieces were put in place by the shuttle's robotic arm. Shuttle crew specialists became on-orbit construction engineers, and these crews were now drawn from an international pool, with Russian cosmonauts riding to space alongside their European and American colleagues. Over a 2-year period, the International Space Station began taking shape. In November 2000, a crew of 2 Russians and 1 American rode to orbit aboard a Russian Soyuz. Though the space station was only partially complete, the crew of 3 became the first people to take up residence on the ISS. Shuttles and Soyuz capsules visited regularly to add more pieces to the orbiting laboratory and to ferry in new supplies. A different type of astronaut was evolving. People were learning to live in space and not just make quick visits. At this time, not all shuttle flights were to the International Space Station. In January 2003, the Space Shuttle Columbia was being prepared for a science mission. The crew of 7 would carry out a range of experiments for both NASA and the European Space Agency. It was the style of research that would ultimately be done on the ISS. Columbia lifted off for a 16-day mission, but there were no spacewalks or other dangerous aspects scheduled, just hardcore science. For 4 of the crew, it was their first trip to space. And while they were enjoying weightlessness, engineers on the ground were reviewing tapes of the launch. A chunk of insulating foam had dislodged from the external tank and had hit the orbiter's left wing. There was nothing anyone could do, so the mission proceeded normally, while ground engineers hoped for the best. During the return to Earth, Columbia disappeared from tracking radar. At the same time in the skies above Texas, an explosion was heard, and debris began raining down. Damage to the wing had been catastrophic, and Columbia had broken up.
Our nation shares in your sorrow. and in your pride. And today we remember not only one moment of tragedy, but 7 lives of great purpose and achievement.
Before the morning had finished, the search for debris from Columbia had started. Though engineers had a reasonable idea of the cause of the disaster, they had to piece together every fragment of wreckage to fully understand the loss of Columbia. The shuttle would resume flying, but NASA experts made a recommendation about its future. It was announced by the President at NASA headquarters.
Our first goal is to complete the International Space Station by 2010. We will finish what we have started. We will meet our obligations to our 15 international partners on this project. In 2010, the Space Shuttle, after nearly 30 years of duty, will be retired from service.
In July 2005, after a hiatus of 2.5 years, Discovery was being prepared for its return to space. During the break, redesign work had focused on the foam insulation covering the external tank. New safety procedures had been established. Flights would only go to the International Space Station where astronauts could wait if it was suspected that a shuttle had sustained damage. And every stage of a shuttle's flight would be closely monitored. In 1988, Discovery had also flown the Return to Space mission after the loss of Challenger. Astronaut Eileen Collins would command the crew of 8. The mission would test on-orbit repair techniques as well as resupplying the International Space Station. Tension in the firing room was palpable. Though each shuttle had been designed for 100 missions, the Columbia inquiry called the shuttle an aging spacecraft, with the odds of losing another orbiter and crew increasing with each flight. Upon arrival at the International Space Station, Discovery did a slow flip to allow the crew on the space station to inspect the craft for any damage to the thermal tiles. At launch, cameras had again picked up insulation foam breaking free from the external tank. This was not supposed to happen anymore, and although there had been no perceived impact, the new protocol called for all shuttles to perform this inspection maneuver. The craft also carried an extension to its robotic arm that allowed a camera to inspect all areas of the thermal protection system. Work on completion of the space station was stepped up. Previously planned scientific missions and a final servicing mission to the Hubble Space Telescope were all cancelled as being too high risk. With every mission now featuring long-duration spacewalks, not just from the shuttle, but also by astronauts living on the International Space Station, training in NASA's Neutral Buoyancy Laboratory became intense, and NASA began referring to the period as the Wall of EVA. Mission specialists would spend years training for the specific tasks that they would have only one opportunity to execute. After Discovery's return to space mission, shuttle flights kept adding to the space station. But almost immediately, dissatisfaction began surfacing within America's scientific community. The Hubble Space Telescope was badly in need of fine guidance sensors, new gyroscopes and batteries, and astronomers were putting pressure on their politicians to allow one last servicing mission to Hubble. In October 2006, NASA's new administrator, Michael Griffin, fudged the safety issue and announced a final repair mission to the Space Telescope. 3 months later, the Advanced Survey Camera, Hubble's most heavily used instrument, went dead. Work on the International Space Station began expanding the role of the shuttle. As well as performing most of the on-orbit construction, the shuttle was now ferrying Russian cosmonauts and European astronauts to and from the ISS, while Americans were riding to orbit on Russian Soyuz craft. The ISS began taking shape, with techniques pioneered on one mission becoming standard on the next. But a new mock-up had been installed in NASA's Neutral Buoyancy Facility. Hubble repair became the focus of one crew destined to be the last to visit the Space Telescope. In May 2009, Atlantis headed for Hubble. After 5 spacewalks, the telescope had been completely refurbished, and astronomy's most valuable instrument was back in business. In July 2011, Atlantis was the last shuttle to fly. It delivered supplies and spares to the ISS. After 12 days, Atlantis returned. It and the rest of the shuttle fleet are now museum pieces.
The Tech Effect shows us how we can unlock tomorrow today.